In the quiet stillness of a clear night, far from any city lights, you stand beneath a dome of stars. The Milky Way spills across the sky like a shimmering river of light, and countless stars glimmer against the darkness. In that moment of solitude, the cosmos feels both boundless and intimate, whispering its ancient secrets. You feel a profound sense of wonder and calm. Above you, the universe stretches on forever, vast and mysterious, inviting you to gaze deeper and deeper. For all of our scientific progress, so much about this universe remains unknown. We have learned how stars shine and how galaxies swirl together in island universes. We've measured the age of the cosmos at nearly 14 billion years. Yet the deeper we look into the sky, the more puzzles we encounter. We find that around 95% of the cosmos is made of something we cannot see or touch, a cosmic recipe of dark ingredients that elude understanding. Our familiar world of planets and stars turns out to be only a thin layer on a vast ocean of mystery. Each discovery we make seems to open a door to new questions. Each answer leads to more profound riddles. Tonight, under this starry canopy, we embark on a journey through some of the greatest unsolved mysteries of the cosmos. In a reflective voyage, we'll explore questions that continue to baffle and inspire. The story of the universe's birth and its sudden inflationary dawn, the invisible matter that holds galaxies together, the unknown energy pulling the universe apart, and the strange physics of black holes where space and time themselves break down. We'll also ponder why the universe exists in the form we know, and even ask whether we are alone amid the stars. These mysteries loom like distant beacons on the horizon of our knowledge, bright, beckoning, and just out of reach. Let us begin our exploration at the very beginning of everything, at the moment of creation itself. Nearly 14 billion years ago, our universe burst into being. In its first instance, it was a seething hot soup of energy, smaller than an atom and unimaginably dense. Then, in a fraction of a second, far less than a blink of an eye, something extraordinary is believed to have occurred. Space itself expanded at a fantastic rate, faster than the speed of light, carrying that tiny spark of creation outward on a swelling wave. We call this phenomenon cosmic inflation. It's a theory that the universe, in its first split second, blew up in size by an enormous factor. This idea of inflation helps resolve several cosmic puzzles. For one, when we look at opposite sides of the sky, they appear almost exactly the same in temperature and composition. Without inflation, there hasn't been enough time since the Big Bang for those far apart regions to exchange any heat or light. They should have evolved separately and ended up different. But if the universe underwent inflation, those regions were once close together before being suddenly thrust far apart. That means they started in contact, reaching a uniform temperature, which is why they look so similar now. Inflation essentially wove a consistent fabric through the young cosmos, making it smooth on large scales, much as stirring a pot of soup evens out its temperature. Inflation didn't just make the early cosmos uniform, it also stretched out any initial curvature of space. This helps explain why the universe today appears overall flat, like a calm, uncurved sheet, rather than obviously curved or warped. In short, inflation set the initial conditions that made our universe so uniform and stable at large scales. Perhaps most remarkably, cosmic inflation could explain the origin of all the structures we see around us. During that tiny moment of inflationary expansion, random quantum fluctuations, the tiny jitter of energy at subatomic scales, were blown up to astronomical proportions. Imagine the universe as a foamy quantum sea at its birth, with little ripples everywhere. Inflation took those ripples and amplified them, seeding slight unevenness in the otherwise smooth spread of matter. Over eons, under the pull of gravity, those slight density differences grew into galaxies, clusters of galaxies, and the vast cosmic web of matter. In this way, inflation connects the very small to the very large. The whisper of quantum uncertainty became the grand design of galaxy clusters and stars. Indeed, the cosmic microwave background radiation, the faint afterglow of the Big Bang, reveals tiny irregularities in temperature across the sky, a direct imprint of those primordial fluctuations that inflation magnified. Without inflation's amplification of quantum ripples, those variations would have been far too minor to grow into the galaxies and galaxy clusters we see today. Yet, despite its elegance, inflation itself remains one of the deepest mysteries. What exactly caused this burst of expansion? We think some kind of exotic energy field, something unlike any force we know today, must have powered inflation. Physicists sometimes call it the inflaton field, a placeholder name for that unknown driver of expansion. But nobody has detected such a field directly. It might have been a high-energy field that suddenly released its energy, heating the young universe and filling it with particles as inflation ended. Exactly how that happened, and why it stopped, we aren't sure. We don't even know for certain that inflation happened at all, though it is the leading theory to explain the early universe. Scientists are searching for clues, like faint gravitational waves imprinted in the afterglow of the Big Bang, that could provide direct evidence of this cosmic growth spurt. So far, no definitive signal has been seen, but experiments are becoming more sensitive, and the hope remains that one day we'll catch a whisper from that first moment, confirming inflation's reality. Inflation also opens the door to mind-bending possibilities. According to some models, inflation might not have been a one-time event confined to our patch of space. Instead, it could be an ongoing process, happening in a vast cosmic expanse beyond our observable horizon. In this picture, what we call the Big Bang was just one bubble of space ending its inflationary phase. Other bubbles might exist far beyond what we can see, each a separate universe with its own properties. Our entire observable universe would be just one such region among countless others, birthed by a greater inflationary cosmos, essentially a multiverse of universes. It's a breathtaking idea that stretches our imagination. We have no way to observe these other hypothetical universes, so for now, the multiverse concept remains speculative. Still, it shows how inflation, if true, may imply that the unknown universe extends far beyond the edges of what we can ever see. In the end, cosmic inflation is a story of profound mystery at the dawn of time. It takes us as close as physics can get to the moment of creation, yet it leaves us with as many questions as answers. Why did inflation start? And what, if anything, came before it? What exactly is the inflationary energy, and how does it fit into the laws of nature we know? Each of these questions reminds us that the beginning of the universe is still shrouded in mystery. What, if anything, came before this explosive inflationary beginning? We don't know. It's possible that the Big Bang was truly the start of time and space, that asking what came before is as meaningless as asking what's north of the North Pole. Yet some theories speculate that our Big Bang could have been one event in a larger cycle. Perhaps the universe undergoes endless expansions and contractions, or perhaps our universe budded off from another parent universe in some grand cosmic landscape. These ideas remain highly speculative, but they remind us that the origin of our cosmos is still cloaked in uncertainty. After inflation's dramatic expansion, the universe was still extremely hot and dense. It was flooded with energy and cooling rapidly, allowing the formation of the first particles of matter. In those early moments, particles of matter and their opposites, antimatter, were born in pairs out of pure energy. Every particle, like a proton or electron, has an antiparticle counterpart, such as an antiproton or a positron, with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a fierce burst of energy. In the young universe, this was happening constantly, particles appearing and disappearing in flashes of light. Under those conditions, you would expect matter and antimatter to almost completely wipe each other out, leaving behind a universe filled with radiation and little else. And yet, that's not what happened. Instead, a tiny imbalance emerged. For every billion or so antimatter particles, there might have been 1,000,000,001 matter particles. That infinitesimal skew, just a few extra specks of matter for every annihilating pair, was enough that when all the matter-antimatter pairs destroyed each other, a small residue of matter remained. That leftover matter became everything we know. Every star, every planet, every atom in your body is made from those survivors of that primordial battle. The question is, why did matter win? What caused the universe to prefer matter over antimatter by that slight margin? This profound mystery is known as the matter-antimatter asymmetry. Our current understanding of physics tells us that, aside from some very subtle effects, nature treats matter and antimatter almost identically. In laboratory experiments, we do see tiny differences in the behavior of certain particles, a phenomenon called CP violation. But these effects are far too small to explain the huge bias toward matter in the cosmos. Something in the conditions of the early universe must have tipped the scales. Perhaps there were exotic processes in those first moments after the Big Bang that created slightly more matter than antimatter. Some theories propose that ghostly particles called neutrinos might have played a role, decaying in a way that favored matter. Others suggest entirely new physics, undiscovered heavy particles or forces that could have generated the imbalance. So far, none of these ideas have been confirmed, and the exact mechanism behind the asymmetry remains elusive. So far, no definitive answer exists. The matter-antimatter imbalance remains one of the most crucial unsolved problems because it underpins our very existence. If nature hadn't slightly favored matter, the universe would contain nothing but light and energy, no stars, no planets, no living beings. Instead, that tiny 1 in a billion difference allowed matter to take hold. It is humbling to realize that everything we see around us owes its existence to a minute violation of symmetry, a quirk of physics we still struggle to understand. Researchers around the world, from giant particle accelerators to delicate lab experiments, are trying to piece together this puzzle. Bit by bit, they explore subtle differences between matter and antimatter, hoping to find clues that will finally reveal why our universe has something rather than nothing. As the universe continued to expand and cool, the era of matter-antimatter annihilation gradually came to an end. What remained was a cosmos dominated by matter, with vast amounts of light, radiation, streaming through space. In those early millennia, the universe was a brilliant, opaque fog of particles and photons mixed together. Eventually, about 380,000 years after the Big Bang, temperatures had fallen enough for protons and electrons to combine into neutral atoms. The fog lifted as space became transparent to light. Photons that had been trapped now could travel freely in all directions. That first light, the afterglow of the Big Bang, is still around us today, faintly filling the universe. We detect it as a dim whisper of microwaves coming from every part of the sky, a relic known as the cosmic microwave background. Imprinted in that ancient light are clues to the universe's infancy, including subtle fingerprints of events like cosmic inflation and the matter-antimatter saga. It is essentially a baby picture of the cosmos, one that scientists continue to study for hints of new physics and new mysteries. As the infant universe expanded and cooled, matter began to clump under the force of gravity. Over hundreds of millions of years, the tiny density fluctuations left by inflation grew into the first stars and galaxies. But when astronomers observe galaxies, they encounter a profound mystery. The stars in the outer regions of galaxies are moving far faster than they should be. In a spiral galaxy, like our Milky Way, stars orbit the galactic center, as if there is far more mass pulling on them than all the visible stars and gas can supply. If the gravity came only from the matter we can see, the shining stars, nebulae, and dust, those fast-moving outer stars would simply drift away into space. Yet they remain bound, as though an invisible glue is holding the galaxy together. Astronomers first suspected this hidden mass decades ago. In the 1930s, Swiss astronomer Fritz Zwicky observed that galaxy clusters were moving as if they had far more mass than was visible, coining the term dunkle materia, dark matter. In the 1970s, astronomer Vera Rubin found a similar effect in individual galaxies. Their rotation speeds did not slow down at the outskirts as expected, implying a huge halo of unseen matter. These early clues pointed strongly to a mysterious new component of the cosmos. This invisible gravitational glue is what scientists now call dark matter. Dark matter does not emit any light or energy that we can detect. It neither glows nor blocks light, like a normal cloud of gas would. It's essentially invisible across the entire electromagnetic spectrum. We infer its presence solely through its gravitational effects. And those effects are dramatic. In galaxies, dark matter appears to outweigh ordinary visible matter by about 5-1. In clusters of galaxies too, we see evidence of a huge hidden mass. Galaxies within clusters move as if there is much more gravity than visible matter alone provides. Even the way massive clusters bend the light from background galaxies, an effect called gravitational lensing, reveals that a great deal of unseen mass is warping space. Roughly a quarter of the universe's total mass energy is thought to be this dark matter, whereas the ordinary atoms that make up stars and planets account for only about 5%. One of the most striking clues for dark matter came from observations of a system called the Bullet Cluster. Here, two galaxy clusters collided at tremendous speeds. Telescopes showed that most of the ordinary matter, the hot, X-ray emitting gas in those clusters, was slowed down and left behind, like two clouds of smoke crashing into each other. But when scientists mapped the total mass in the system using gravitational lensing, they found that the bulk of the mass had essentially passed straight through the collision, hardly interacting at all. It's as if two invisible clouds of matter flew through one another without friction, while the visible matter, the gas and stars, slammed together and was held back. The mass detected by its gravity ended up separated from the ordinary matter, indicating that the majority of matter in those clusters does not interact through light or collision, only through gravity. This observation provided strong evidence that dark matter is real and distinct from normal matter. But what exactly is dark matter? We know what it is not. It's not made of the familiar atoms that form people, planets, and stars. It must be some other kind of particle or object that doesn't emit light and barely interacts with normal matter. Many scientists suspect it could be a new type of subatomic particle, perhaps a heavy relic of the Big Bang that carries no electric charge. These hypothetical particles have whimsical names like WIMPs, weakly interacting massive particles, or axions. For decades, huge detectors deep underground have been built to catch a glimpse of dark matter particles passing through Earth. Tanks of ultra-pure liquid, sensitive crystals, and other instruments lie in wait for a rare impact. A dark matter particle striking an atomic nucleus inside the detector. So far, no unmistakable signal has appeared. Likewise, telescopes have searched for high-energy radiation that might be released if dark matter particles annihilate each other in space, and particle accelerators, like the Large Hadron Collider, have tried to create dark matter in high-energy collisions. Yet dark matter continues to elude us, slipping through our experiments like a ghost. The continuing absence of a discovery has even led some researchers to ask if dark matter is truly a substance at all, or if we might need to revise our laws of gravity. A class of theories called modified gravity tries to tweak the rules of gravity to explain galaxy rotations and other phenomena without invoking invisible mass. However, no modified gravity theory has yet succeeded in matching all the evidence. The behavior of galaxies, the dynamics of galaxy clusters, the patterns in the cosmic microwave background, and dramatic collisions like the bullet cluster all point to some form of unseen matter. For now, the vast majority of experts remain convinced that dark matter is real. We simply have yet to identify it. Dark matter stands as one of the most significant unsolved puzzles in science. It is literally all around us. Billions of dark matter particles might be passing through your body each second, yet it has never been directly detected. This mysterious substance shaped the large-scale structure of the cosmos. Without dark matter's gravitational pull, galaxies and clusters might never have formed as they did. It is the unseen scaffolding of the universe, the shadow framework upon which the visible world is built. Discovering its true nature would profoundly deepen our understanding of what the cosmos is made of. Until then, we are left with the tantalizing knowledge that most of the matter in the universe is invisible and unknown. And now, having pondered this hidden mass that binds the cosmos together, we turn to an even stranger cosmic ingredient, one that does not pull things together, but instead pushes everything apart. At the turn of the 21st century, astronomers made a stunning discovery about the universe's expansion. Ever since Edwin Hubble in the 1920s found that galaxies are rushing away from us, scientists assumed that this expansion should be slowing down over time. After all, gravity pulls matter together, so the collective gravity of everything in the cosmos should be tugging at the expansion, gradually decelerating it. For decades, the big question was whether that slowdown would eventually stop the expansion, perhaps even lead to a recollapse of the universe, or whether the universe would expand forever at a steadily reducing pace. To find out, two teams of astronomers in the late 1990s set out to measure the cosmic slowdown by observing distant stellar explosions called Type Ia supernovae. These supernovae serve as standard candles with known intrinsic brightness, allowing scientists to gauge their distances by how dim they appear. By comparing those distances with how much the light from the supernovae has been stretched, redshifted, by the expansion of space, researchers could infer the expansion rate of the universe at different times in the past. They expected to find that very distant supernovae from earlier epochs appeared a bit brighter than predicted for a constant expansion, indicating that expansion was faster in the past and has been slowing down. Instead, the observations revealed something completely unexpected. The distant supernovae were dimmer, and thus farther away, than the scientists anticipated. It was as if, over the billions of years that their light travelled, the universe's expansion had not been slowing at all. It had been speeding up. This was an extraordinary surprise. The expansion of the universe, it turns out, is accelerating. Galaxies are receding from one another faster and faster as time goes on. The teams that discovered this accelerating expansion initially questioned their findings, suspecting perhaps some error or intervening dust that made the supernovae appear fainter. But as more data rolled in, the evidence only grew stronger. Other methods and observations began to agree. The universe really is accelerating. In 2011, the leaders of those teams received the Nobel Prize in Physics for this discovery. The cause of the acceleration was attributed to something we now call dark energy. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. It's dark, not because it is dark like night, but because it is mysterious. An unknown form of energy, or effect, that doesn't emit light. We only became aware of it through its influence on cosmic expansion. Today, dark energy is thought to make up roughly 70% of the total content of the universe, far outweighing dark matter, about 25%, and ordinary matter, around 5%. In a sense, dark energy acts like a kind of anti-gravity on the largest scales, pushing the fabric of space outward. What could dark energy be? One leading idea is that it's a built-in property of space itself. Einstein's theory of general relativity allows for a constant energy associated with empty space, often called the cosmological constant. If that's the case, then as the universe expands, new space comes with more of this vacuum energy, and the overall push continues unabated. This simple model, a constant energy of the vacuum, fits the astronomical observations fairly well so far. Intriguingly, Einstein himself introduced a cosmological constant term in his equations a century ago to balance the universe against collapse, then later called it his greatest blunder when evidence showed the universe was expanding. Yet now, the concept has reappeared as a core explanation for dark energy's effect. If dark energy is truly this constant vacuum energy, it means every cubic meter of empty space holds a tiny amount of energy. The amount is extremely small, we don't notice it in daily life, but because space is so vast and growing, it dominates the universe. However, there are other possibilities. Dark energy might not be perfectly constant. Its strength could change over time. Some theories propose a force or field, nicknamed quintessence, that fills space and varies slowly, rather than a fixed energy per volume. So far, no clear evidence of such changes has been found. Dark energy behaves very much like a constant, but ongoing observations are watching carefully for any sign that this mysterious energy evolves. Dark energy poses deep theoretical puzzles. If it is the energy of empty space, a cosmological constant, our best quantum physics theories wildly overestimate how much vacuum energy there should be, by many orders of magnitude larger than what we observe driving the acceleration. This discrepancy between prediction and observation is perhaps the biggest unsolved problem in fundamental physics. On the other hand, if dark energy is due to a new field or force, it raises other tough questions. Why did this energy become dominant only in the relatively recent cosmic past? And how might it connect to physics as we know it? At this point, We simply don't know. We are, quite literally, in the dark. We do know, however, how dark energy behaves on large scales, at least roughly. It seems to be spread evenly through space, unlike matter, which clumps into galaxies and clusters. And as the universe expands, dark energy's influence doesn't fade away like matter does. It remains constant, or even gets proportionally more important as space grows. Around 5 or 6 billion years ago, the universe had expanded enough for dark energy's repulsive effect to overcome the cumulative pull of gravity from matter. Since that time, the expansion has been accelerating, with dark energy driving galaxies apart ever more rapidly. Looking ahead, if dark energy continues at the same strength or grows even stronger, the future of our universe will become increasingly desolate. Distant galaxies will recede faster and faster until they slip beyond the horizon of what we can see. Trillions of years from now, an observer in our galaxy, or its remnants, might look out and see no other galaxies at all, just endless darkness stretching in every direction. All the other island universes will have been driven out of view. Stars within our gravitational locale will eventually burn out, and new stars will no longer form because gas supplies will be exhausted. This is sometimes called the Big Freeze, or heat death scenario, a future where the cosmos grows cold and empty as expansion marches on relentlessly. Could anything else happen? There are even more dramatic possibilities, though current data don't indicate they will come to pass. If dark energy were to grow stronger over time, it could lead to a big rip. In that extreme scenario, the repulsive force would, far in the future, become so overwhelming that it shreds galaxies, stars, and eventually atoms themselves, tearing apart the fabric of the cosmos. On the other hand, if dark energy were to fade or turn attractive, cosmic expansion might slow down again. It could even halt and reverse, ending in a gravitational big crunch that collapses the universe back into a hot, dense state. At the moment, however, observations suggest dark energy is constant, making the Big Freeze the most likely fate on unimaginably long timescales. Dark energy underscores how little we truly understand about the cosmos at a fundamental level. It was completely unanticipated and still defies explanation by current physics. Unraveling its nature is one of the foremost challenges in cosmology and particle physics today. New telescopes and surveys are mapping the expansion of the universe in greater detail, hoping to catch subtle clues about dark energy's identity. Upcoming missions like the European Euclid Space Telescope and the Vera Rubin Observatory on Earth will chart galaxies and distant supernovae, seeking any sign that dark energy's influence has changed over cosmic time. One intriguing hint of potential new physics is the so-called Hubble tension, a persistent discrepancy between the expansion rate as measured in the nearby universe and the rate inferred from the patterns in the early cosmos. It's possible this mismatch is due to measurement issues, but it could also be telling us that our cosmological model is incomplete, perhaps revealing subtle changes in dark energy over time, or the influence of some other unseen cosmic ingredient. Perhaps we will discover tiny deviations in dark energy's behavior that hint at new physics, or perhaps we will confirm it as an immutable feature of spacetime. Either outcome would be profound. For now, dark energy remains a towering enigma, a dominant presence in the cosmos that we scarcely understand. Having explored the unseen matter that holds galaxies together and the mysterious energy that drives the cosmos apart, we find that the universe's story is still rife with unknowns. Even as we use the word dark to label these phenomena, we must admit that the term merely signifies our ignorance. The deeper we peer into the cosmos, the more we realize how much remains hidden from us. Some of the most intriguing mysteries now lead us to the extremes of gravity and spacetime, to objects so strange that they challenge our understanding of physics itself. Our journey next brings us face to face with these cosmic enigmas. Black holes. Black holes are the universe's most enigmatic objects. They are regions where gravity is so intense that not even light can escape. The very idea of a black hole, a place of no return, is both fascinating and frightening. They form when massive stars collapse under their own weight, or when smaller black holes merge into bigger ones. In the centers of galaxies, including our own Milky Way, lurk supermassive black holes, millions or billions of times more massive than the Sun. A black hole's boundary, the event horizon, is like an invisible membrane wrapping the region of no escape. Once anything passes inside, a star, a planet, a spacecraft, it cannot come back out. For a long time, black holes were purely theoretical constructs predicted by Einstein's equations of gravity. Many scientists doubted they could really exist in nature. But over the past decades, evidence for black holes has become overwhelming. Black holes also distort time and space in extreme ways. To a distant observer, an object falling toward a black hole appears to slow down and fade, never quite crossing the event horizon. Yet from the falling object's own perspective, it plunges inward in a finite time. Moreover, the gravity near a small black hole is so intensely non-uniform that it can stretch and squeeze objects, a process sometimes called spaghettification, because a falling astronaut, for instance, would be stretched long and thin like a noodle. It's a lethal, mind-boggling effect of gravity run amok. When a star, much more massive than our Sun, exhausts its nuclear fuel, it can no longer resist the inward pull of gravity. The core collapses, and if the mass is great enough, no known force can halt the collapse. A black hole is born, packing several suns' worth of mass into an incredibly small volume. There are also black holes of other sizes. Some are the remnants of those collapsed massive stars, typically a few times the Sun's mass. Others are supermassive giants found in the centers of galaxies, containing millions or billions of solar masses. These supermassive black holes, like the one in our Milky Way's core, might have grown from smaller seeds over billions of years, or perhaps formed through the direct collapse of huge amounts of gas in the early universe. We're not entirely sure. In fact, observations of very distant quasars, extremely bright galactic cores powered by supermassive black holes, reveal that some black holes had already reached colossal sizes when the universe was only a few 100 million years old. How they grew so big so fast remains an open question, hinting that black holes might have formed or evolved in ways we don't yet fully understand. We have observed stars orbiting an unseen, compact object at the center of our galaxy, whipping around at incredible speeds. Strong evidence of a huge mass crammed into a tiny space. Exactly what we'd expect for a black hole. We've detected the subtle bending of starlight as it passes near an invisible mass, the light curving as if around a massive, unseen object. In 2015, scientists heard faint ripples in spacetime, gravitational waves, from the collision of two distant black holes, confirming not only that black holes exist, but that they merge in spectacular cosmic events. And in 2019, humanity got its first picture of a black hole's shadow. The Event Horizon Telescope collaboration revealed a bright ring of hot gas circling the dark silhouette of a supermassive black hole in the galaxy M87. These observations have cemented black holes as real components of our universe, not just mathematical curiosities. Yet even as we confirm their existence, black holes remain deeply mysterious. They push physics to its limits. At the heart of a black hole, general relativity, our theory of gravity, predicts a singularity, a point of infinite density where space and time as we know them cease to exist. In truth, this signals that our equations have broken down. We don't really believe nature produces actual infinities. Rather, we suspect that some new physics, likely a theory uniting gravity with quantum mechanics, is needed to describe what happens in those extreme conditions. So far, we lack a complete theory of quantum gravity to resolve this. Even the event horizon itself poses puzzles. Quantum theory suggests that black holes are not completely black. Stephen Hawking famously showed that they should emit a very faint thermal glow, now called Hawking radiation, due to quantum effects near the horizon. If this is true, black holes can slowly evaporate over mind-boggling spans of time, radiating away their mass bit by bit. But this idea leads to a paradox. What happens to all the information about the matter that fell into the black hole? In principle, if the black hole evaporates entirely, does the information simply vanish? Such a loss of information would violate a fundamental tenet of quantum physics. This information paradox has led to intense debate and research. Some believe that perhaps the information is somehow encoded in the Hawking radiation in a highly scrambled form, or that black holes might leave behind some stable remnant, or that the very notion of information needs rethinking in these extreme scenarios. Solving this paradox is not just about black holes. It could have far-reaching implications for our understanding of quantum mechanics and spacetime. Black holes also stir the imagination because they represent the boundaries of the known. What lies beyond an event horizon? Is it truly an end? Or could it be a doorway of some sort? General relativity allows for exotic solutions like wormholes, hypothetical tunnels through spacetime, and one can't help but wonder if nature exploits anything like that inside black holes. Most physicists are skeptical that traversable wormholes exist, especially naturally occurring ones. Nevertheless, black holes are the closest thing in reality to the fantastic portals of science fiction. Some theorists have even speculated that a black hole could, under certain conditions, spawn a new baby universe on the other side. A wild idea that underscores how little we know about these cosmic objects. While such speculations are far from proven, they capture the sense that black holes are at the frontier of our knowledge, where space, time, and the very fabric of reality behave in ways we barely grasp. As we study black holes, we are essentially probing the extremes of nature. Each new observation, whether it's capturing gravitational waves from merging black holes or imaging the turbulent plasma around an event horizon, provides us with clues about gravity under the most intense conditions. Black holes have already taught us so much, yet they guard many secrets. To truly decipher what goes on in those hidden depths, and to answer the riddles they pose, we may need a breakthrough in physics. Perhaps that will come with a successful union of quantum theory and gravity, a theory that could unlock not only the secrets of black holes, but also mysteries of the very early universe. In that sense, black holes are not just cosmic curiosities. They are signposts toward a deeper understanding of reality. As we gaze into the abyss of a black hole, we are also gazing at the edge of human knowledge, hopeful that one day we will illuminate the darkness. There is another curious cosmic mystery that often emerges when we consider the universe's ability to host life. Many of the fundamental constants and laws of nature seem to be just right, as if finely tuned for the development of complexity. For example, if the force of gravity were slightly stronger or weaker, Stars might burn too fast or never ignite. If the strength of electromagnetism or the masses of fundamental particles were even a few % different, atoms might not form stable molecules, or stars might not produce the heavy elements life depends on. It's as though the universe, out of many imaginable possibilities, ended up with a set of physical parameters that fall within a narrow Goldilocks range suitable for life as we know it. Why should this be so? Some argue it could be mere coincidence. After all, we wouldn't be here to notice if the universe weren't habitable. This reasoning is known as the anthropic principle. Among a possibly vast ensemble of different universes or different regions with varied physical constants, we naturally find ourselves in one that is capable of supporting observers. In other words, perhaps countless other sets of physical laws are possible, but they are sterile, and only in this rare combination do galaxies, stars, planets, and life emerge. Other scientists search for a more fundamental explanation. Maybe a deeper theory of physics will one day show that these constants could not have been otherwise, that there is an underlying principle forcing them into the life-friendly range. So far, however, we don't have a definitive answer. We are left marveling at the fortunate parameters of our cosmos, whether they arose by chance, necessity, or something else entirely. It's a mystery that straddles the line between science and philosophy, a reminder that even the very existence of a hospitable universe raises questions we've yet to answer. In all our cosmic explorations, we have so far encountered only one place where life is known to exist: our own planet Earth. The emergence of life from non-living matter is itself a profound mystery. On the early Earth, somehow chemistry transitioned into biology. Collections of molecules became self-replicating, evolving organisms. We still don't fully understand how this happened. Was it an extremely rare fluke of chemistry, or a nearly inevitable process under the right conditions? Scientists are trying to recreate aspects of this in laboratories and study ancient evidence, but the exact recipe that sparked life remains elusive. Yet, once life got started on Earth, it proved remarkably tenacious and inventive, eventually giving rise to creatures capable of wondering about the universe, like us. The question that now haunts our observations of the stars is, are we unique? Or is the universe teeming with life, scattered on countless worlds? With hundreds of billions of galaxies, each containing billions of stars, it seems almost arrogant to assume that Earth would be the only cradle of life. Many of those stars have planets. In fact, over the past few decades, astronomers have discovered thousands of exoplanets orbiting distant suns. Some of these planets are in the so-called habitable zone, where temperatures could allow liquid water to exist. Water, as far as we know, is a key ingredient for life. We've found planets that are Earth-sized and at the right distance from their stars. Some lie only tens of light years away. The raw ingredients for life appear to be common throughout the cosmos: water, carbon-rich molecules, energy sources. This gives us reason to suspect that the universe might be bio-friendly, that simple life could potentially arise in many places. And yet, despite all the vastness and all these possibilities, we have not, so far, seen any clear sign of life beyond Earth. We've listened for signals from intelligent civilizations with radio telescopes. We've scanned the atmospheres of exoplanets for the chemical fingerprints of biology, and we've searched within our own solar system for even the tiniest microbes. The results so far, only silence and mystery. This silence, in the midst of apparent cosmic plenty, is sometimes called the Fermi paradox. If the universe is capable of hosting so many civilizations, where are they? Why haven't we detected even a whisper of alien life? There are many potential answers, none confirmed. Perhaps life is exceedingly rare, and we really are essentially alone in our galaxy. Or perhaps simple life is common, but intelligent life, capable of building radios or spacecraft, is vanishingly uncommon. It could also be that civilizations are out there, but not broadcasting in ways we can perceive, or they may be separated from us by vast distances or great stretches of time. It's conceivable that life exists in forms we wouldn't easily recognize, or on worlds that we cannot easily observe. Every possible solution to this puzzle has profound implications. Closer to home, we continue to explore our neighboring worlds for hints of life beyond Earth. Mars, which long ago had liquid water on its surface, could have hosted microbial life in its ancient past, and if so, perhaps some traces remain in the soil or locked in the ice. The icy moons of Jupiter and Saturn, like Europa and Enceladus, harbour subsurface oceans beneath their frozen crusts. These dark oceans, warmed by internal heat, could be comfortable habitats for living organisms such as microbes or simple sea creatures. Scientists have even detected complex organic molecules and plumes of water vapour spewing from Enceladus, hinting at a chemically rich ocean environment. If we discovered even a single microbe beyond Earth, whether fossilized in Martian rock or alive in an alien ocean, it would tell us that life is not a one-off miracle confined to our world, that it can take root elsewhere. On the other hand, if we scour world after world and find nothing, that would also be telling. It would suggest that life might indeed be exceedingly special, perhaps requiring a rare combination of conditions or events that are hard to come by. As we stand under the starry sky, we can't help but wonder about our cosmic neighbours, if any exist. Perhaps somewhere in the galaxy, under the light of an alien sun, other beings gaze at their night sky and wonder the same thing. The search for life beyond Earth is not just a scientific endeavour, it's a deeply human quest. To know whether we have company in this universe, or whether the duty of understanding and appreciating this vast cosmos falls solely to us. For now, we have no answers, only questions that spur us to continue exploring. We send out spacecraft and listen with giant antennas into the dark, hoping for a sign, a faint radio whisper, a peculiar chemical signature in an exoplanet's atmosphere, or a microbial fossil in a Martian rock. Any hint that says, "You are not alone." Thus far, the universe has revealed nothing definitive. If there are living secrets out there, they remain well hidden. The night is calm and infinite above us. We drift further into the cosmic deep, our minds still aglow from the mysteries we've already explored. The silence of space is not empty. It's filled with our questions, echoing out into the dark. As we continue our voyage, a new wonder emerges before us, the possibility that our universe is not alone. The stars around us seem almost to whisper it. In the vastness beyond the edge of what we can see, could there be other realms, other universes, as real as our own? We imagine an endless ocean of worlds, a multiverse of possibilities stretching out forever, worlds without end, hidden just out of reach. Picture the universe we know as a single bubble, drifting in a limitless sea of spacetime. Now imagine countless other bubbles floating alongside ours, each a separate universe with its own stars, galaxies, and perhaps life. This is one vision of the multiverse, an infinite expanse where every bubble, is a cosmos unto itself. In some of those universes, the laws of nature might be familiar. In others, gravity could be stronger, or atoms might never form. There could be realms where time flows differently, or where no galaxies ever coalesce. Yet if space never truly ends, if creation is boundless, then somewhere far beyond the horizon of our telescopes, these other worlds might exist, unseen but real. Some scientists believe the multiverse isn't just possible, but might even be necessary to explain our own existence. They point out that our universe has just the right conditions for life, a lucky combination of physical laws and constants. Why is it so perfectly tuned? One answer is that if there are countless universes, each with random settings, it's no surprise that at least one would happen to have the right conditions for life. And we, as observers, naturally find ourselves in such a universe. Indeed, many of the fundamental numbers in nature seem finely balanced. If the force of gravity were slightly stronger or weaker, or if the charge of the electron or the mass of a proton were even a few % different, stars might not have stable lifetimes, or atoms might not form the way they do. The odds of all these parameters being just so by chance in one universe feel astronomically small. But if there are countless universes, each with different values, then it's not surprising that some will randomly have the right recipe for complexity and life. We find ourselves in one of those, because only in such a universe could observers exist to marvel at the fact. This reasoning, known as the anthropic principle, becomes more palatable in a multiverse. Our cosmos may not be unique or designed, just selected by the necessity of our presence. It is a humbling idea, one that simultaneously makes us feel small and yet part of something unimaginably grand. Not everyone is comfortable with this idea. The multiverse challenges our notions of evidence and testability. By its nature, these other universes might be forever beyond our reach, cut off from ours entirely. If we cannot ever visit or detect them directly, are they truly a scientific concept, or just philosophical speculation? Some physicists criticize the multiverse hypothesis because it seems to offer every possible answer. If anything strange is observed, one could say, somewhere in the multiverse it happens, which makes it hard to falsify. And yet, others argue that just because something is hard to observe doesn't mean it isn't real. They're searching for subtle clues, clever tests that might hint we're part of a larger ensemble of universes. It's a profound debate. Is the multiverse a bold extension of cosmology, or an unfalsifiable leap of faith? For now, it remains an intriguing possibility that stretches our imagination to its limits. What might the multiverse look like if we could see it from a higher vantage? Some cosmologists picture an eternal, inflating space where universes are constantly budding off like new bubbles. In the first tiny fraction of a second after the Big Bang, our own cosmos underwent a sudden dramatic expansion, cosmic inflation, that blew up a tiny region into the vast universe we see today. But inflation might not have been a one-time event. In some models, it's an ongoing process in a grander space. Quantum fluctuations could make inflation stop in one patch, creating a bubble universe like ours, while continuing elsewhere, and then another bubble forms, and another, an endless foam of universes popping into existence. Our universe would just be one bubble where inflation ended and stars and galaxies formed. Elsewhere, beyond our observable horizon, other bubbles are doing the same. Some may have different physics, different fundamental constants or particles, if the underlying conditions vary from bubble to bubble. It's a vast and almost dizzying view of reality. Not one Big Bang, but innumerable Big Bangs, giving birth to innumerable worlds. If these bubble universes exist, could they ever bump into each other? If the multiverse is like a cosmic ocean of bubbles, one might imagine two bubbles colliding. What would that do? Perhaps such collisions are extremely rare, but they could leave scars. Scientists have actually searched our sky for hints of this. A telltale pattern in the afterglow of the Big Bang, the cosmic microwave background radiation. This background is mostly uniform noise, but there are tiny irregularities. One especially puzzling feature is a large cold spot, a patch of sky cooler than expected. Some have wondered if this cold spot might be a bruise, the mark of another universe's bubble brushing against ours in the distant past. The idea sounds like science fiction, and indeed it's far from confirmed. The cold spot could turn out to be caused by an unusually big void in our own universe, or simply a statistical fluke. Yet the possibility lingers. If further data supported it, that cold blemish in the sky could be the first evidence that our cosmos had a cosmic neighbour. Just the thought of that is astonishing, that the imprint of another universe might be subtly written across our sky, waiting for us to decipher it. Meanwhile, the concept of a multiverse tempts our imagination in other ways too. Think of infinity. If space truly goes on forever, even just as one infinite universe, then anything that can happen will happen, somewhere out there. There could be another planet so much like Earth that even its continents and clouds are familiar. Far beyond the reach of any telescope, there might be a galaxy that is a twin of our Milky Way, and on one of its planets, creatures identical to us, living out lives with only the slightest differences. This isn't magic, but mathematics. In an infinite expanse, the arrangements of matter must eventually repeat by chance. So even within a single endless universe, one gets a kind of multiverse of possibilities. Now consider multiple separate universes on top of that. The variety could be beyond anything we can truly picture. Every outcome of every story might be realized somewhere. Worlds where dinosaurs never went extinct. Worlds where no stars ever lit up, leaving eternal darkness. Worlds that begin, flash into existence for a second, then collapse back into nothing. And others that expand and thrive for trillions of years. Worlds without end. There is also a mind-bending facet to the multiverse that comes not from cosmic inflation or bubble collisions, but from the strange realm of quantum physics. In the microscopic world, particles don't behave like tiny billiard balls. They exist in a haze of possibilities, only settling into a definite state when observed or measured. One interpretation of this mystery, the many worlds, interpretation of quantum mechanics, suggests that whenever a quantum event has multiple possible outcomes, all outcomes actually occur, each in its own separate branch of reality. In essence, the universe splits into parallel versions for each outcome. If this is true, then the multiverse is not a distant cosmic sea, but right on top of us, intertwined with every decision and every random quantum jump. In one world, an electron went left. In another, it went right. In one branch of the multiverse, you chose a certain path. In another, you made a different choice. In countless parallel worlds, every life path you could have taken is played out in full. Unlike the bubble universes, which are separated by vast stretches of space, or perhaps by extra dimensions, these quantum parallel worlds would overlap with ours, yet remain completely invisible and inaccessible. We would never know the other versions of ourselves, or see those alternate histories. They would be like ghost universes running alongside our own. Still, the implication is profound. Reality wouldn't be a single track, but a cosmic library containing every book, every story, a branching tree of universes, spawning trillions of new realities every moment. Some thinkers have tried to categorize these bewildering possibilities into levels or types of multiverse. One type is simply an extension of our own space. Regions so far away we'll never reach them, but with the same physics as here. Another type involves distinct physical laws, like other bubbles where gravity or atoms behave differently. And the many worlds quantum branching is yet another type, where universes overlap in a tree of possibilities. It seems wherever we push, reality offers more, a multi-layered infinity of universes. How do we live, knowing there might be infinite versions of us out there? It's a philosophical conundrum. On one hand, it could make our choices feel less unique. After all, if in another universe you made a different choice, perhaps every possible version of you exists somewhere. But one could also see it as oddly comforting. The road not taken is taken, somewhere, by another you. So in a sense, no possibility is ever lost. Every dream, every path, exists in some branch of reality. Yet for us, here and now, we experience only this one thread of life. We cannot step into those parallel fates. They are forever out of reach, sealed off by quantum separation. They serve more as a tantalizing suggestion that reality has more layers than we perceive, rather than a practical extension of our world. Some people wonder if this idea of many worlds means everything that can happen must happen in some universe. If that's true, it is both marvelous and eerie. It means that somewhere there is a universe where things turned out very differently for you. Perhaps vastly better, perhaps worse. Do those alternate yous have any significance to you? Probably not, except to broaden your perspective. We realize that our personal reality is just one slice of a much larger pie. The scope of existence would be far greater than what we see. This concept can change how we view meaning. If infinite versions of you exist, does it diminish your importance or multiply it infinitely? One might argue it doesn't change this life at all. You still have to make choices and find purpose here. Alternatively, one might feel a strange relief that somewhere another self gets to experience the paths you didn't take, as if collectively you experience it all. These are deep waters where science meets philosophy and even spirituality. The multiverse, in all its forms, asks us to imagine beyond our single universe. It's a scene almost beyond comprehension, yet strangely calming, as though knowing that existence is so vast takes away some of the urgency of our daily worries and replaces it with awe. We might imagine, fancifully, that if we had a higher dimensional view, we would see a vast tapestry of universes, like a foam of countless bubbles, glinting in a cosmic dark. Each universe would glow with its own internal light, bursts of stars, separated from others by immense gulfs or by unseen dimensions. The multiverse beckons with an ultimate question. Is this reality the only reality, or just one realm among many? As we float here in the quiet night, letting that question resonate, we find our sense of wonder only deepens. This multiverse concept is in some ways the ultimate extension of a lesson we've learned over centuries. Whenever we thought we were the center of everything, we discovered we weren't. Earth was not the center of the solar system. Our sun turned out to be one star among billions in the galaxy. Our galaxy itself one among countless others in the universe. Now the multiverse suggests even our entire universe might be just one of many. It's a humbling idea, one that both magnifies creation and diminishes our centrality within it. But humble or not, it fills us with awe. We see ourselves as part of a possibly infinite mosaic. Our universe, with all its galaxies and wonders, could be just one tile in an endless cosmic tapestry. And yet, that knowledge, or speculation, also reminds us how precious our particular world is. Out of a myriad worlds, this is the one we know and love. How remarkable that we can even ask what lies beyond it. Will we ever find hard evidence of other universes? Perhaps someday, subtle patterns in the background radiation or in gravitational waves will give us hints that our universe had siblings. Physicists are attempting creative experiments, even simulating bubble universes in laboratories to see what observable signatures might arise. It's a long shot, as one scientist said, a search for something we thought we could never test. But humanity has a stubborn habit of probing the impossible. Even if direct proof remains elusive, the multiverse will live on in our theories and imaginations. It shows up in our fiction, in our dreams, in those moments when we stare up at the starry sky and wonder, what if? It is a concept that, true or not, expands our perspective tremendously. It reminds us that the cosmos could be far, far larger than the slice we see. Real or not, thinking about the multiverse has already changed us, teaching us both humility and imagination. It makes us appreciate how special our universe is to us, while simultaneously suggesting that reality might be endlessly diverse. We feel small, yet part of something infinite. We feel perplexed, yet full of wonder. And wonder is what carries us onward. From these countless worlds beyond our own, our journey now turns inward, toward the nature of reality itself. We've imagined space beyond space. Now we ask, could everything we experience be something other than it appears? Is it possible that our entire cosmos is not the base reality we assume, but some kind of grand illusion or artificial construct? In whispers and late-night speculations, this idea has been called the simulation hypothesis, the conjecture that the universe we live in and everything we experience might be the product of an immensely sophisticated computer program or a cosmic dream. Imagine, just for a moment, that late one night, a message appears in the sky telling you, this is all a simulation. How would you feel? Suddenly the solid world around you, the trees, the sky, the very ground, might seem less certain. It sounds like pure fantasy, but the idea that our reality could be virtual is being seriously pondered by scientists and philosophers. We live each day assuming the world is real and fundamental, never questioning the fabric of existence. Yet what if beneath the surface of all we see, there lies code and computation? What if we, unknowingly, are characters in some grand cosmic software? Take a moment to absorb that possibility. Look around at your world, the trees, the sky, the stars above. They feel solid and real. You live, love, learn, all under the assumption that this is base reality. But if we were characters in an immensely sophisticated simulation created by an advanced intelligence, would things feel any different? Perhaps not. Our lives would still feel just as rich. This notion that the universe is a kind of programmed reality sounds like science fiction, but it's also a legitimate scientific hypothesis that some respected thinkers take seriously. A popular argument for the simulation hypothesis came from philosopher Nick Bostrom in the early 2000s. He essentially suggested that at least one of three possibilities must be true. 1. No civilization ever reaches the technological capability to create ancestor simulations, simulated universes with conscious beings like us. Or, 2, civilizations do reach that level, but, for whatever reason, choose not to run such simulations. Or 3, advanced civilizations do run many simulations, so many that simulated conscious beings would vastly outnumber the original, real beings. If that third scenario is the case, then statistically, it's far more likely that we ourselves are among the simulated minds rather than the original biological minds. In simpler terms, if future, or alien, civilizations can create countless detailed universes on their computers, the odds are that our reality is one of those simulations, rather than the one original universe. It's a startling piece of reasoning. Suddenly, the question, are we real or virtual, became a serious topic of debate, not just a plot for a movie. Bostrom's logic gained traction in part because of the rapid progress we see in our own technology. In just a few decades, we've gone from simple computer games with blocky graphics to virtual reality and sophisticated simulations of worlds. If humans can already create immersive artificial environments on a small scale, imagine what a civilization 1,000 or 1,000,000 years more advanced could do. They might simulate entire universes, complete with self-aware beings who have no idea they are inside a creation. Every improvement in our video games and VR experiences makes it easier to envision how a simulated reality could be indistinguishable from a real one. We can even foresee our own descendants perhaps running such simulations of their ancestors, a thought that blurs the line between future and past, and between reality and illusion. But what would motivate someone to simulate an entire universe? Perhaps scientific curiosity, a desire to see how physics might unfold under slightly different conditions, or to observe the rise and fall of civilizations. It could be a form of research, like running a vast experiment. Or maybe the purpose is entertainment. Advanced beings might create worlds the way we create movies or games, for storytelling or amusement. Some have even speculated it could be done for educational or spiritual reasons, a way for souls or minds to learn lessons within a simulated environment. These ideas verge on the metaphysical, blurring science with philosophy, but they show the richness of thought that the simulation hypothesis encourages. There are other reasons people point to when considering the simulation idea. For one, the more we study the universe, the more it seems to be based on mathematical laws. Perhaps that's not a coincidence, but a feature of the universe being fundamentally information-based. If I were a character in a computer game, said one cosmologist, I would also discover eventually that the rules seemed completely rigid and mathematical. That just reflects the computer code in which it was written. Furthermore, concepts from information theory keep appearing in physics. Remarkably, a theoretical physicist named James Gates, while studying supersymmetry equations, found something curious. Embedded within the complex math were patterns identical to computer error-correcting codes, the same kind of codes that make your web browser work reliably. Gates remarked that this discovery gave him a stark realization that he could no longer dismiss the idea of the universe being a form of computation. It was as if he'd glimpsed, in the equations of fundamental particles, a faint imprint of a programmer's handiwork. Such observations make the simulation hypothesis enticing. But many experts are skeptical and urge caution. Just because the universe can be described mathematically doesn't prove it's a simulation. Maybe reality is inherently mathematical, and finding a code-like pattern in one set of equations might be a mathematical quirk rather than literal evidence of coding. Prominent physicist Lisa Randall has voiced strong doubts arguing that the simulation argument is built on many assumptions about unknown advanced beings and their motives. She questions why a superintelligent species would even bother simulating ancestors or universes. Perhaps it's a rather human-centric idea to assume they'd be interested in making virtual worlds of us. Other critics point out that the simulation hypothesis may be untestable in any definitive way. It could be a philosophical rabbit hole more than a physical theory. Still, the notion refuses to fade because it is fascinating and, surprisingly, not easy to dismiss outright. Some researchers have even proposed ways to look for experimental evidence that we might be living in a simulation. One idea is that if the programmers have limited computing power, they might economize by rendering the universe on a discrete lattice or grid, rather than as a perfectly smooth continuum. If so, at extremely high energies, or on very large scales, we might detect signs of this underlying grid. For example, cosmic rays, high-energy particles from distant space, could exhibit an unusual cutoff or directional pattern, suggesting spacetime isn't perfectly continuous, but has a grain to it. Scientists have actually considered looking at the distribution of cosmic ray energies and arrival directions for such anomalies. So far, no such evidence has been found, and nature appears smooth as far as we can tell. And who's to say a sophisticated simulation would even have such obvious glitches? Some people jokingly point to déjà vu, that strange feeling of having experienced a moment before, as a potential glitch in the matrix, or they cite the Mandela effect, where large groups of people remember an event or detail differently from how it actually is, as evidence of edits in reality. These are playful notions, and almost certainly just quirks of human memory and perception. True physical evidence of a simulation remains elusive, yet proving the opposite, proving that the universe is definitively not a simulation, might be even harder. As some philosophers note, if we were in a simulation, any evidence we find could itself be planted or part of the simulation's programming. It's a logical trap. We might never be able to be sure. If we are in a simulation, who or what is the simulator? This question leads to many speculations. Perhaps it's a future version of humanity, running simulations of their ancestors, us, out of curiosity or research. Essentially, our creators would be future humans treating us as a kind of historical archive. Or maybe it's an alien civilization, experimenting or playing. Some have even whimsically suggested that the creator of our universe might be a young student or hobbyist in another, higher reality. Some teenage hacker in the next universe up, as one physicist quipped. We ourselves create simulated worlds in our computers. Think of characters in video games or virtual worlds, without considering ourselves deities. By analogy, our simulators might not be all-powerful or divine, just technologically advanced. This comparison was highlighted by philosopher David Chalmers. If we create a detailed simulation of, say, a city with AI inhabitants, we don't think of ourselves as gods relative to them, even though we control their reality. Similarly, our simulators could be quite mortal and ordinary in their own universe, even if they have godlike power over ours. The simulation idea also connects in interesting ways to age-old philosophical and spiritual questions. If we truly are digital beings in a computer, what does that imply about concepts like an afterlife or resurrection? Some have noted it opens strange possibilities. If our minds are just data, perhaps they could be saved and reloaded. As Gates mused, a program can be restarted as long as the computer isn't destroyed. In theory, a future advanced being could copy or rerun the simulation, effectively bringing everyone back to life or rewinding events. It's a provocative parallel to religious ideas of rebirth or resurrection, only with technology as the mechanism. And what about the end of the universe? If it's a simulation, might it simply be shut off one day? Neil deGrasse Tyson once playfully asked, "What if there's a bug that crashes the entire program?" scientificamerican.com. Perhaps the Big Rip, or heat death, could be the equivalent of our simulation running out of resources or being turned off. These comparisons show how the simulation hypothesis provides a new lens to revisit deep questions. Who are we? Why are we here? What happens when it all ends? Suddenly those can be framed in terms of code, programmers, and system reboots. Amidst all this grand speculation, a practical question arises. Does it really matter if we're in a simulation or not? One might conclude that even if we are living in a grand illusion, the experiences we have and the relationships we form are no less profound. Real or simulated, life feels real to us, and perhaps that is enough. After all, if you cherish someone, that love is genuine to you, whether or not the universe runs on code. If you stand before a mountain and feel awe, that experience moves you regardless of what fundamental level it arises from. In short, the meanings we find and the values we hold don't necessarily depend on whether reality is base level or a simulation. Our joys and sorrows, our aspirations and accomplishments, they all matter to us here and now. If the simulation hypothesis does anything, it perhaps reminds us to have a bit of humility. It suggests that reality could have layers beneath layers, and what we take for granted might be just one level of a deeper structure. Many spiritual traditions and philosophers have taught that the world we perceive might be an illusion. The Hindu concept of Maya, for instance, implies that the world as we see it is not the ultimate reality. Plato's allegory of the cave imagines people living chained in a cave, seeing only shadows on a wall and mistaking them for real objects. Centuries later, René Descartes mused about an evil demon that could be deceiving us with a fake external world. In various ways, thinkers through the ages raised the question, how can we be sure our experiences are real and not a grand deception? The simulation hypothesis is a high-tech, modern spin on those age-old doubts, swapping the demon or the dream for a supercomputer, but echoing the same fundamental question. It shows that even as our scientific understanding advances, some philosophical mysteries remain. They just get new vocabulary. In a way, if our universe is a kind of cosmic dream, one might wonder about the dreamer. Are we the dream of some higher mind or advanced intelligence? The Chinese philosopher Zhuangzi famously dreamt he was a butterfly, then awoke to question if he was a man who had dreamt of being a butterfly, or a butterfly now dreaming he was a man. Likewise, if our lives are part of some grand simulation, is there a clear boundary between the dream and the dreamer? It's possible that even the beings running our simulation are themselves part of another simulation, layers upon layers reflecting worlds within worlds. We may never know the ultimate reality, if there is one at all. Sometimes people wonder, if this is a simulation, could the creators ever let us know? Would there be a day when the sky might literally crack open to reveal the game masters? Or would it be subtler? Maybe they observe us without interference, like characters in a story, and choose never to announce themselves. If the simulators are benevolent or scientific, perhaps they prefer not to disturb our natural development. If they are indifferent, we might simply carry on, never learning the truth until the simulation ends. These questions border on the theological. They show how the simulation hypothesis can become a canvas for all kinds of existential speculation. Perhaps the ultimate takeaway is humility. There could be layers to existence beyond our current comprehension. We shouldn't be too quick to assume we know the full story of reality. But at the same time, maybe we shouldn't worry too much. Whether or not our universe is real, in an absolute sense, it is real to us. We still bleed, laugh, and fall in love. A simulated sunrise is just as warm and beautiful to the one beholding it. In the end, maybe the difference between base reality and a perfect simulation makes no practical difference to our lives. We awaken each day and face the choices before us regardless. Real or virtual, we must live meaningfully and kindly in the world we have. Our advice might even be, as one scientist half joked, go out and do really interesting things so the simulators don't shut you down. In other words, live fully, simulation or not. And so the simulation hypothesis remains a tantalizing, unsolved mystery, inviting us to question the boundary between reality and illusion. One might say it's less about proving we are simulated and more about expanding our minds to entertain new possibilities. It encourages a kind of cosmic open-mindedness. We see that things may not be exactly as they appear, and that in itself is a valuable realization. Now, whether our universe is singular and physical, or one of many, or even a simulation, we still find ourselves bound by certain cosmic rules: distance and time, cause and effect. Our feet are on the ground of this reality, whatever it may fundamentally be, and we look out at the vast distances between stars and at the relentless flow of time carrying us forward. In our next exploration, we ask, could there be shortcuts through space and time, hidden bridges that connect far-flung corners of the cosmos, or even different eras? Perhaps there are secret tunnels in the fabric of the universe that would let us travel instantly to distant galaxies, or gateways that loop time back on itself. These ideas, wormholes and time travel, are staples of imaginative fiction. They entice us with the hope of transcending the limits nature seems to set. Do they exist outside of human imagination? Let's find out. Let's begin with wormholes, those hypothetical tunnels through space-time. Imagine you have a sheet of paper representing our universe, and two dots on opposite ends of the sheet representing two distant stars. Normally, to travel from one star to the other, you'd have to journey across the sheet, a long, slow trip across space. But what if you could fold the paper so the two dots touched? A shortcut appears. Punch a hole through the folded paper, and the two far-apart points become directly connected. In theory, that's what a wormhole could do. It's a bridge that folds space, allowing a shortcut between locations that could be light years apart. This idea first emerged from Einstein's general theory of relativity. In 1935, Albert Einstein and Nathan Rosen realized that the equations of gravity allowed, in principle, a tunnel-like structure connecting 2 points in space, essentially a shortcut through an extra dimension of space. This hypothetical tunnel is known as an Einstein-Rosen bridge, or more colloquially, a wormhole. At the time, it was a curious mathematical oddity. The simplest version, in the context of a black hole solution, seemed to pinch off too quickly for anything to actually pass through. It was not traversable. But the concept was planted. Scientists and dreamers did not let the idea go. Over the decades, they wondered, could something keep a wormhole open? Normally, gravity makes space-time want to curve in on itself. A wormhole, if formed, would tend to collapse almost instantly under its own gravity. To hold a wormhole open, one would need some form of exotic matter that has negative gravitational effect, like negative energy density. Such stuff isn't known in classical physics, but quantum physics allows for tiny amounts of negative energy in certain situations, for example in the Casimir effect between closely spaced plates. The speculation is that if an advanced civilization could gather enough negative energy or otherwise engineer the fabric of space, they might prop a wormhole open like a tunnel with reinforced walls, making it traversable. No one knows if this is actually possible. We have never seen a wormhole, and the kinds of negative mass energy needed are purely hypothetical. It remains a speculative possibility within general relativity's equations, albeit requiring conditions that are extremely exotic. If a traversable wormhole did exist, it would be an astonishing tool. We could step through a door and emerge on a planet orbiting another star instantly without crossing the light years in between. The far side of the galaxy could be as near as a step through your front door. Imagine the freedom that would offer, the whole cosmos accessible without a spaceship. Humanity could explore the entire universe almost as easily as stepping into another room. What might it feel like to travel through such a cosmic shortcut? Perhaps as you approach the mouth of a wormhole, it would appear as a shimmering sphere or a whirlpool of distorted light, bending the stars behind it. With a deep breath, you cross the threshold. Maybe there's a strange lurching sensation, or a moment of darkness and silence, and before you know it, you step out the other side. The scene before you is completely different. A new star hangs in a foreign sky. Unfamiliar constellations glitter around it. Perhaps an alien sun is rising over an alien landscape. A journey of light years, accomplished in seconds. It would be the ultimate voyage, like a dream where distant places merge together, where one door can open on the other side of the galaxy. As of now, wormholes remain theoretical. We don't know of any naturally occurring ones. Some speculative ideas suggest there might be microscopic wormholes popping in and out of existence in quantum foam, but none large enough or stable enough for a person to traverse. Still, scientists keep the flame of possibility alive in their equations. And interestingly, recent research has drawn intriguing connections between wormholes and quantum physics. There's a conjecture in theoretical physics, abbreviated EPR, which suggests that wormholes, Einstein-Rosen bridges, ER, might be deeply connected to quantum entanglement, EPR after Einstein-Podolsky-Rosen. In a poetic sense, an entangled pair of particles, two particles mysteriously linked so that what happens to one seems to instantly affect the other, could be thought of as being connected by a tiny wormhole in a higher dimensional space. This idea is still very speculative, but it has led to some fascinating work. In late 2022, for example, a team of physicists used Google's cutting-edge quantum computer to simulate a very simple wormhole-like scenario. They created a system of entangled quantum bits and managed to send a piece of information from one side to the other in a way that was mathematically analogous to it, passing through a tiny wormhole. To be clear, this wasn't a real space tunnel. It was more of a translation of a quantum process into gravitational language, but it was a striking demonstration of the concept that what looks like a wormhole in gravity theory can correspond to quantum information processes. The fact that quantum experiments can mimic wormhole behavior hints at a profound link between the geometry of spacetime and the physics of information. Some even speculate that spacetime itself may be a kind of web woven from quantum connections, nature's way of coding gravity. If that's true, wormholes and entanglement might be two faces of the same underlying reality. Wormholes spark the imagination so much that even if they don't exist naturally, we can't help but dream about creating them. The idea of engineering a hole in the fabric of space-time to bridge distant points is far beyond our current science. It might remain forever in the realm of thought experiments. but considering it has value, it pushes our understanding of general relativity and quantum theory to their limits and forces us to confront what is or isn't allowed by physics. It's the kind of problem that might lead to new insights, even if the original goal, build a wormhole, proves unattainable. And it undeniably inspires the public. Wormholes feature in countless science fiction stories as portals for interstellar travel. We yearn for them to be real, because they represent liberation from the vast distances that separate us from the rest of the universe. Interestingly, wormholes blur into the subject of time travel when we consider their full implications. A wormhole, in theory, could not only connect two distant places in space, it might also connect two different times. This is where things truly become surreal. Imagine a wormhole with two ends, often called mouths. If one mouth stays here on Earth and the other mouth is placed on a spaceship that takes a high-speed journey or sits deep in a strong gravitational field, and then is brought back, the two ends of the wormhole will have experienced time differently due to relativistic time dilation. Perhaps one mouth has aged only a few years, while the other experienced decades. In that case, someone entering the younger mouth could emerge from the older mouth in the past relative to when they entered. In essence, the wormhole could become a time machine. This idea was popularized by physicist Kip Thorne in the late 20th century, when he and colleagues seriously analyzed whether the laws of physics would allow such a construction. They concluded it requires exotic matter to hold the wormhole open, but if you had that, the time travel aspect might indeed work. Time travel fascinates and troubles us because of the paradoxes it invites. Nearly everyone has heard of the classic grandfather paradox. Suppose you go back in time and somehow prevent your grandparents from meeting. Then you wouldn't be born, which means you couldn't have gone back to do anything, which means your grandparents would meet, which means... and so on. It's a logical contradiction, a loop with no consistent solution. There's also the bootstrap paradox, or ontological paradox, where an object or piece of information has no origin because it is brought back from the future and becomes itself in the past. For example, imagine a scientist from the future goes back and gives young Beethoven a book of his own compositions, and Beethoven copies them down and becomes famous. Who originally wrote the music? It came from nowhere, looping through time. These paradoxes suggest that changing the past is problematic at best, impossible at worst. Many physicists suspect that nature has built-in safeguards against time travel to the past. Stephen Hawking, for instance, conjectured a chronology protection principle. Basically, he thought the laws of physics might prevent closed time loops from forming, thus protecting causality. He even humorously illustrated this by hosting a party for time travelers. In a famous light-hearted experiment, Hawking once threw a champagne party for any future time travelers who might see his invitation, but he sent out the invitations after the date of the party. On June 28, 2009, he arranged balloons, champagne, and snacks in a college hall at Cambridge and waited for a long time, but nobody arrived. He hoped perhaps thousands of years in the future, someone might find the invitation and use a wormhole time machine to come back to the party, proving time travel possible. But alas, no visitor came. Hawking sat alone and eventually left, concluding wryly that this was experimental evidence time travel to the past is unlikely. Either it's not possible at all, or no one in the future ever figures it out, or cares to visit us. It was a playful event, but it highlighted a serious point. Thus far, we've seen no tourists from the future. Yet interestingly, the equations of general relativity themselves do not strictly forbid time loops. As early as 1949, mathematician Kurt Gödel, a friend of Einstein, found a cosmological solution to Einstein's equations, a universe with a sort of overall rotation, in which time became a closed loop. In Gödel's universe, one could in theory travel far out in a certain direction and eventually arrive in one's own past. This model doesn't resemble our actual universe. We see no evidence that the cosmos is globally rotating like that. But it was a stunning proof of concept. Relativity permits time travel solutions in principle. Later on, other exotic proposals surfaced. For example, physicist J. Richard Gott suggested that cosmic strings, hypothetical ultra-dense filamentary objects left from the early universe, could, if two of them zoomed past each other at nearly light speed, create conditions for closed time-like curves. By flying a spaceship in a certain path around these rapidly moving strings, one might emerge at an earlier time than one started. These scenarios demand circumstances far beyond anything we know to exist, and cosmic strings themselves remain hypothetical. But they demonstrate that the only real barriers to backward time travel might be practical ones, not absolute law. While travelling to the past is fraught with paradoxes, travelling to the future is not only possible in theory, but has been observed, albeit on a small scale. In fact, we're all constantly travelling into the future at the normal rate of 1 second per second. But relativity tells us we can stretch that rate. If you want to leap ahead significantly, you can exploit time dilation, move very fast, or stay near a strong gravitational field, and your clock will tick slower relative to those far away. For instance, astronauts on the International Space Station age just a tiny bit less than people on Earth, because time runs a bit slower for them in orbit, thanks to their high speed and slightly weaker gravity. If you took a journey at near light speed and returned, you might find that decades have passed on Earth, while perhaps only a few years passed for you. This isn't paradoxical at all. It's just how time works in relativity. In effect, you've travelled into Earth's future. The catch, of course, is that you can't come back to your original present. You can only go forward, and then you're stuck there. Still, it's fascinating that nature allows a form of one-way time travel. It suggests that our usual experience of time is not absolute. It can stretch and compress. So far, human-made time jumps are infinitesimal, fractions of a second for astronauts. But if one day we had the technology to travel close to light speed, we could send someone to, say, the year 3000, and have them return, looking only a little older than when they left. The grandfather paradox and others arise only if you can loop back. And modern physics has been exploring whether such loops could be paradox-free after all. A few years ago, an undergraduate student, Jermaine Tobar from UQ in Australia, published a mathematical analysis suggesting that if time travel is possible, events would adjust themselves to avoid inconsistencies. In his model, you could travel to the past and attempt to change something. But reality would find a way to converge to a self-consistent outcome. To use a topical example that was given, imagine a time traveler goes back to stop a disease from spreading. If they succeed, then there's no disease to motivate them to go back. So in theory, that's a paradox. But in this model, perhaps their very actions cause the disease to spread in a different way. They might prevent patient 0 from catching it, only to unintentionally introduce the virus elsewhere, ensuring it still spreads. Whatever the time traveler does, they can't actually prevent the outcome they set out to prevent. Events flex and bend, but land on the same result, maintaining consistency. In essence, this hypothesis allows time travel, but not the changing of established history. A bit like storylines where you going back was always part of history, and you end up fulfilling, not altering, the past. The math checked out, as the supervising physicist put it, but whether physics in the real universe would permit even that scenario is unknown. From a narrative standpoint, It's almost like the universe could protect itself from paradoxes by self-correcting any alterations. Try as you might to rewrite history, some twist of fate intervenes to keep the broad strokes the same. It's a compelling idea because it offers a resolution to paradoxes. Time travel might exist, but you'd be constrained in such a way that you can't create an inconsistency. In fact, you never did create one, because your actions were always part of the consistent timeline. However, this is just one theoretical model. It hasn't been tested experimentally. How could it, without actual time machines? And it still doesn't tell us how to travel through time. It just speculates what would happen if we could. Thus far, every design for a device that could send people back in time remains speculative. Ideas range from using rotating black holes to enormous spinning cylinders, the Tipler cylinder concept, to cosmic strings in particular configurations. All require conditions, mass densities, energies, or materials, far beyond anything we can handle, and some require an infinite universe or never-ending rotation. In other words, they're not practical. As one scientist remarked, the time machines scientists have devised so far exist only on paper. They're interesting thought experiments in general relativity and quantum physics, but building them is another matter entirely. Perhaps the universe does have a chronology protection mechanism after all. For instance, quantum effects might intervene to destroy wormholes at the moment they could become time loops, or the required exotic matter might be fundamentally impossible to accumulate in large amounts. Many physicists suspect something like that must happen, given the chaos unrestricted time travel would introduce. And so, time travel to the past remains a staple of fiction and theoretical musings, not a part of everyday life. No tourists from the future are sighted at ancient events, as far as we know. For now, wormholes and backward time travel remain firmly in the realm of speculation, but they have undoubtedly captured our collective imagination. We endlessly write stories and make films about stepping through portals or hopping in time machines. These concepts resonate deeply with us, perhaps because they promise a form of freedom from the limits of distance and time. They symbolize our desire to explore and to correct regrets, to instantly reunite with loved ones, far away or long gone. The very fact that we dream of wormholes and time machines shows the creativity of the human spirit and our refusal to accept boundaries without at least testing them in our minds. Even if wormholes or time machines never materialize in reality, exploring these ideas expands our sense of what might be possible. We stretch the fabric of reality in our imagination, testing its weave for hidden openings. And while we haven't torn through to new realms yet, we've caught a glimpse of how flexible space and time could be under extreme conditions. That in itself is a kind of enlightenment, realizing that the universe might permit far stranger things than our everyday experience suggests. In pushing against these limits, we deepen our understanding of physics. For instance, studying wormholes has led to insights in quantum gravity, and pondering time travel has sharpened our understanding of causality. The future remains unwritten. Perhaps one day, far in the future, our descendants will discover how to manipulate space-time in ways we cannot yet imagine, creating wormhole subways to distant stars, or finding clever loopholes that allow some form of time travel without paradox. Or perhaps the fabric of reality will keep its gates firmly closed, and we will find other, more conventional ways to roam the stars, slowly, or via generation ships, or suspended animation. In either case, our fascination with these ideas will continue to inspire us. Our journey now takes a contemplative turn, from moving through space and time to the nature of time itself. We've imagined bending space and looping time. Now we consider whether time might itself be cyclical, Is the flow of time a one-way street? Or could it, on the grandest scale, loop back on itself? In other words, is there an eternal return, a cosmic cycle that repeats endlessly? This next mystery invites us to step even further back and view existence on the largest scales, where the end might meet the beginning. Time is often compared to a river, flowing in one direction from past to future. But if time were cyclic, perhaps it is more like a great wheel or an orbit, always moving forward, yet eventually circling back to the start. The ancient symbol of the Ouroboros, a serpent eating its own tail, comes to mind, an emblem of cycles and eternal return. The idea of cosmic time loops, or an eternal return, is ancient and deeply embedded in human thought. Long before modern science, people in many cultures imagined that time might be circular. Many cultures embraced cosmic cycles. In India, Hindu philosophy speaks of vast ages called kalpas and yugas, cycles of creation and destruction, turning like a cosmic wheel without beginning or end. The Hindu and Buddhist conception of reincarnation, individual souls living, dying, and being reborn, is a reflection of this cyclical pattern on a human scale. In the West, the ancient Stoic philosophers pondered the eternal return, suggesting that the universe might periodically be consumed in a great fire, a conflagration, and then reborn anew, with the same events playing out again and again. We find echoes of cosmic cycles in myths around the world, from the Norse idea of Ragnarok, a world-ending battle followed by a renewal of the world, to various indigenous cosmologies, where time is seen as a repeating circle. Such visions carry a mix of hope and fatalism. Hope that existence doesn't simply end, but renews eternally. And fatalism in that everything that happens might be fated to repeat, exactly with no escape. In our current scientific understanding, the universe as we see it began 13.8 billion years ago in a Big Bang, and it has been expanding ever since. For much of the 20th century, scientists debated whether this expansion would continue forever or eventually reverse. If gravity were strong enough, perhaps the expansion would slow, stop, and then the universe would recollapse into a big crunch, potentially followed by a rebound, a new Big Bang from the ashes of the old. That was one way to imagine a cosmic time loop, an oscillating universe with infinite cycles of bang expansion crunch, bang expansion crunch. However, in the late 1990s, observations of distant supernovae revealed that the expansion of the universe isn't slowing down, it's speeding up, apparently driven by a mysterious dark energy. If this acceleration holds and nothing intervenes, our universe will not crunch. It will expand forever, growing colder and more dilute, likely approaching a state of heat death where all stars have died out. That scenario is a one-way street, time like an arrow flying forward into darkness. Yet, not all cosmologists are convinced that's the end of the story. Some have proposed new models to allow the idea of cycles to persist despite the observations. Consider the possibility that the Big Bang was not the ultimate beginning, but merely one phase in an endless cycle of cosmic death and rebirth. If you could somehow stand outside time and watch the grandest panorama, you might see our universe expand and evolve, then eventually fade or dissolve, only to trigger a new Big Bang, the cosmos born again from its own ashes. In a sense, the universe could behave like a phoenix, eternally rising from its own destruction. One prominent cyclic theory comes from the mind of physicist Roger Penrose. He proposed an intriguing model called conformal cyclic cosmology. In Penrose's vision, The universe iterates through infinite cycles, or eons. How does this work, given perpetual expansion? Penrose's key insight is that in an extremely far future, when the universe has expanded so much that all matter decays and all black holes evaporate, nothing with a fixed scale remains, only massless particles like photons moving through an almost empty space. Without mass, and without any meaningful clocks, the concepts of distance and time become fuzzy. In a way, the vastly expanded, empty universe can be mathematically scaled down and identified with a kind of next Big Bang. In more technical terms, the geometry of the universe at the infinite end of time could be transformed via a conformal rescaling to become the geometry of the extremely hot, dense beginning of a new universe. Thus, the remote future of one eon becomes the Big Bang of the next. According to CCC, our Big Bang might have been the continuation of a previous eon's far future thin, spread-out state. Penrose and his collaborators have even claimed to find tentative evidence of this in the cosmic microwave background. They reported seeing concentric low-variance circles and Hawking points, spots that might be the final Hawking radiation bursts of massive black holes from a previous universe. These claims are controversial and not widely accepted by the cosmology community, with many arguing the supposed signals could just be random noise. But it is fascinating that such tests are even being attempted. If any evidence of a before the Big Bang were confirmed, it would upend our concept of time's arrow on the ultimate scale. Apart from CCC, other scientists have explored whether the Big Bang itself might have been a big bounce, the rebound from a previously collapsed state. In these models, the universe's expansion eventually slows and reverses. Maybe dark energy is not constant or will decay, leading to a big crunch. But instead of an absolute end or singularity, quantum effects kick in to avoid infinite density, and the universe bounces into a new expansion. The result is an oscillating cosmos. Expand, contract, bounce, expand again, potentially forever. Each cycle might begin with similar conditions, or perhaps with some differences. Such models, often arising in loop quantum gravity and other theories, avoid the problem of a true origin by positing an eternal series of universes, one after another. Whether our universe will ultimately recollapse or not is uncertain. Current data leans toward endless expansion. But these bounce scenarios show one way a time loop on the grandest scale could occur. Now, if the universe does cycle in some way, it raises profound questions. Are we fated to repeat this exact life an infinite number of times? Or could each cycle be slightly different, perhaps progressively evolving? Some modern cyclic models, like certain ekpyrotic scenarios involving colliding brains in string theory, envision that each new cycle might not be a carbon copy of the last. The physics could reset with some random variations, or the conditions could differ just enough that history doesn't repeat exactly. Others, like the strict eternal return concept of the Stoics, or certain interpretations of CCC, suggest everything will happen again just as it did, down to the smallest detail, because the fundamental conditions are the same. If every cycle were truly identical, then each of us has lived this life an infinite number of times before, and will live it again an infinite number of times in the future. It's a staggering idea that can be either comforting or horrifying. It implies a kind of immortality, but also a kind of imprisonment in the same story. We can't know which, if any, of these is true. Different theories paint different pictures, one of exact repetition, another of endless renewal with variation. It leads to a personal thought experiment that famous philosopher Friedrich Nietzsche once posed. If you had to live this life over and over for eternity, would that be a blessing or a curse? How would you live if you knew you must live this exact life again and again, forever? It's a daunting proposition with no easy answer. Would each moment become precious beyond measure, knowing it returns eternally? Or would the weight of infinite repetition rob actions of meaning? Perhaps you might strive to make choices you could embrace for eternity. Or perhaps you'd seek a way to break free from the cycle, if that were even possible. The eternal return idea doesn't have a definitive answer, but it urges us to reflect deeply on our values and choices. It makes us consider what we might change if we could loop back, and why we aren't making those changes now, in the one life we know we have. From a physics perspective, the idea of time loops confronts the arrow of time question. We know that on the scale of everyday life, time has a direction. Entropy, disorder, increases. Eggs break, but don't unbreak. We remember the past, but not the future. For a true cosmic loop to occur, something unusual must happen to entropy. Essentially, there would need to be a reset of the entropy count in each cycle. Otherwise, each successive cycle would accumulate more disorder, and the universe could never repeat its initial state. In cyclic models, mechanisms are proposed to handle this. For instance, in a big crunch followed by a big bang, perhaps all structures get crushed, and any memory of the past arrangement is destroyed, allowing a low entropy rebirth. In Penrose's CCC, he requires that as the universe empties out, particles lose their mass and clocks lose meaning. So the concept of entropy itself becomes irrelevant, making the end state conformally equivalent to a low entropy beginning again. These are clever ideas, but they are speculative and not yet empirically confirmed. Even if the universe cycles, it's likely that no information, and certainly no memory, carries over from one cycle to the next, at least not in any obvious way. We in this universe have no recollection of a previous cosmos, aside from those contested patterns in the microwave background that Penrose points out. If countless universes have come and gone before ours, we've been none the wiser. No one remembers a previous cycle any more than we remember a time before our birth. So, practically speaking, whether time is cyclic or not, we experience each cycle as a unique, one-way journey. That's an interesting twist. The universe as a whole might loop, but for the inhabitants of each cycle, time would still feel like it's moving forward, and only forward. The loop is so large we don't see the curve. Ultimately, what do we make of the possibility of cosmic time loops and eternal returns? On the practical side, current evidence doesn't favor a literal loop. It seems the universe will expand indefinitely, at least with our present understanding. But our understanding could change. Cosmic time loops remain a tantalizing possibility that theory allows, even if observations haven't found them. On the philosophical side, the idea of recurrence can be both haunting and enlightening. If everything we do will happen again and again, one could view that as stripping meaning. Why strive if it all repeats exactly? Or as imparting eternal significance to each moment, since you will experience this moment for eternity, better to make it a good one. It's like an existential litmus test. Some find the concept inspiring, encouraging them to live in such a way that they would be content to repeat their life. Others find it terrifying, implying no ultimate progress or novelty. In many ways, whether or not the universe literally cycles, the reflection it offers us is valuable. It forces us to consider what it is we truly want out of existence. If you knew this set of experiences was to recur forever, would you change anything now? Would you handle your relationships, your creative pursuits, your day-to-day choices differently? These questions have no right answer, but they push us towards self-understanding. And if the universe does not cycle, if we have one run only, then that also encourages us to make the most of it. Either way, thinking about cosmic time loops brings our focus back to the present moment and its importance. Time is one of the deepest mysteries of all. We still don't fully understand why it has an arrow, whether that arrow could ever reverse, or if the concept of beginning and end even applies on the grandest scales. Modern cosmology suggests a one-way evolution, with a beginning in the Big Bang and perhaps an endless expansion. But we must admit that the very beginning is not well understood, and the far future could hold surprises. Our mathematics allows cycles and loops. Nature, so far, seems to prefer one-directional time. Yet nature has surprised us before. As we peer into these questions, we find our sense of mystery revitalized. There is something almost poetic about the idea of an eternal return. It's as if the universe, like a great story, might enjoy a rereading of itself, over and over. It's late in our journey now. We've roamed through some of the most mind-bending, unsolved mysteries of the cosmos. We've imagined infinite other universes beyond our own, and questioned whether our reality is but a simulation. We've toyed with the fabric of space and time, envisioning tunnels that bridge light years and loops that could send us to yesterday. We've contemplated time as a circle that forever turns. Each of these ideas leaves us with more questions than answers. And still, there is more ahead. We haven't even touched on the invisible forces that shape the cosmos, the dark matter holding galaxies together, the dark energy driving acceleration, nor the puzzle of how life emerged and whether we are alone in the universe. The unknown universe holds many more secrets, waiting in the dark, like distant stars we have yet to see. Our journey doesn't end here. In the space between what is known and unknown, we feel the pull to continue, to seek the next question, the next wonder. The night remains deep and full of mysteries. Gently, our minds prepare to voyage onward, carrying the echoes of what we have pondered. The cosmic adventure goes on, and we move forward, ever curious, into the next chapter of discovery. We begin in the hush of twilight, as the last glow of day yields to a dome of night. Far from city lights, the sky unfolds as a dark tapestry pricked with countless stars. In this vast quiet, the cosmos reveals itself, a river of milky light arching overhead, constellations glittering like old friends. Our ancestors once gathered under these same stars, eyes wide with wonder. Without telescopes or science, they wove meaning from the patterns above, filling the night with stories. In those ancient nights, the sky became a canvas for myth. A swath of pale light, the Milky Way, might be seen as spilled milk from a divine mother, a luminous ark of creation. To the Greeks, it was the milk of Hera, strewn across the heavens in a moment of cosmic nursing. To the Egyptians, it was a heavenly Nile, a celestial river flowing with cow's milk from the goddess of the sky, nourishing the world below. Others knew it as the path of souls, a shimmering road in the night, leading departed spirits to the afterlife. Beneath this glowing band, early humans felt the presence of something greater and spun tales to explain its glow. They looked at the clustering of stars and imagined patterns, the constellations. A mighty hunter draws his bow in the winter sky, forever chasing the celestial bull. A great bear pads around the North Star through the seasons. Twin brothers, a scorpion's tail, a hero with a lion's skin. Each arrangement of stars became characters in cosmic dramas. Every point of light was part of a story, each constellation a memory of gods, heroes, and monsters placed into the heavens. These myths gave the cold, distant lights a warm, human meaning. The night was not empty, it was alive with narrative. Yet myths did more than entertain. They were our first cosmologies, early attempts to make sense of an overwhelming universe. In the absence of modern knowledge, imagination filled the void. Many cultures envisioned how the cosmos began in a language of symbolism. Some spoke of a cosmic egg, a primordial orb that cracked open to birth the world, an egg of golden light hatching heaven and earth. Others imagined a world tree, its branches holding aloft the sky and its roots reaching down into the underworld, uniting all realms. In Norse sagas, a great ash tree, Yggdrasil, bound together the heavens, earth, and underworld, with stars twinkling in its highest boughs. In these stories, the universe was a living thing, a great organism, or an intentional creation by divine hands. Such visions were grand and filled with wonder. A giant serpent might encircle the world, biting its tail, marking the horizon of all that is. A turtle might carry the weight of the earth on its back, swimming through a cosmic sea. In ancient China, it was said that a giant named Pangu cracked open a cosmic egg, creating the sky and earth from its halves. The Maya people envisioned a great cosmic crocodile swimming in a primordial sea from which the world was born. Different as these stories were, they shared a common wonder about how everything began. In myth, the boundaries of reality were defined by imagination. There were heavens above and underworlds below, layered realms beyond the reach of ordinary life. Though each culture's tales were unique, they all grappled with the same questions. Where did everything come from? What are those lights in the sky? Who are we in this immense expanse? In the stillness of ancient nights, under the glittering canopy, humans felt both fear and comfort. The stars were constant, seasonal markers guiding migrations and harvests, but also mysterious and unreachable. By telling stories about the stars, people found familiarity in the unknown. The sky became a decorated ceiling of a world they understood, at least in part, through mythic imagination. It made the infinite feel intimate. The cosmos was not a cold void. It was a realm of gods and ancestors, a cosmic stage where meaningful events unfolded and influenced life on Earth. One can imagine a family in ancient times, gathered under the stars around a flickering fire, as an elder points to the sky. He tells of gods, animals, and heroes among those lights, turning the fearful unknown above into a story they can hold on to. In sharing such tales, our ancestors found comfort and connection beneath the same vast heavens that awe us today. Time moved on, and those ancient cosmic visions slowly evolved. The rise of philosophy and early science brought new interpretations. The Greek philosophers began to seek natural explanations for celestial phenomena. They measured the movements of stars and planets, trying to discern patterns and principles. Still, even as reason took root, wonder remained. One philosopher, Anaxagoras, living in the 5th century BCE, dared to suggest a radical idea, that life might not be confined to Earth, that the seeds of life could be scattered throughout the universe. He imagined the heavens were full of living seeds. Panspermia, he called it, meaning seeds everywhere, that occasionally fell to earth to sprout life. In a time when gods were thought to hurl lightning and dictate harvests, this was a bold, visionary thought. Such early sparks of scientific insight were rare and often met with disbelief, yet they marked the dawn of a new way of seeing the cosmos. Over millennia, myth and observation together paved the way for understanding. The sky's secrets began to unfold through mathematics and telescopes. We learned that the stars are not God's campfires, but distant suns blazing across unimaginable gulfs. The earth was not the center of all things, but one world among countless others. Ancient myths gradually gave way to new cosmic stories, those crafted by science. And yet, even as we replaced constellations of gods with galaxies and nebulae, the deepest questions persisted. The myths answered in metaphor what science now faces with evidence and theory. How did the universe begin? How did life arise? Are we alone in this vast expanse, or do other minds gaze back at the stars from distant worlds? Where does the cosmos end, or does it go on forever? These questions echo the old curiosities of our ancestors, now explored with the tools of modern inquiry. The ancient skywatchers stood in awe of the unknown. Today, despite all our knowledge, we too stand in awe, perhaps even more so. Each answer science finds spawns new questions, and some mysteries remain as enigmatic as ever. We have journeyed from seeing patterns of gods in the sky to sending spacecraft beyond our planetary cradle. We have peered back in time to nearly the dawn of the universe. And yet the cosmos still holds its secrets close. Our next steps in this journey of understanding will take us into the realm of those enduring mysteries, the origin of life, the search for company in the stars, and the question of the universe's very limits. So now, let us gently leave behind the realm of ancient legends and step into the cosmic dark with modern eyes. We trade stories of gods for equations and hypotheses, but the sense of wonder remains our faithful guide. In that spirit, we turn to a mystery that bridges the divide between myth and science, the possibility that life itself has a cosmic origin. High above Earth, a faint streak of light traces the path of a falling star. But imagine, for a moment, that within that meteor's heart lies a tiny traveller, a living spore, dormant and protected in a cocoon of rock. For ages it drifted in the cold vacuum, carried silently between the stars. Now, drawn by Earth's gravity, it plunges through the atmosphere. Fire chars the meteor's exterior, but deep inside, the little spore survives the fiery entry. The meteor lands in a quiet pond, dissolving slowly, and the sleeping microbe awakens. Finding liquid water and nutrients, it begins to grow and multiply. Life, once afloat in space, takes root on a new world. This scenario is the essence of panspermia, the idea that life can spread through the cosmos, sowing one planet with the living material from another. The word itself means seeds everywhere. It is a hypothesis that suggests life might not have begun anew on every world where it exists, but could travel between worlds, hitchhiking on comets, asteroids, or dust. In this view, planets are not isolated crucibles of Genesis, but part of a galactic ecosystem, exchanging the ingredients of biology. Life becomes a wandering seed and the universe a vast garden where those seeds might bloom wherever they find fertile ground. For a long time, panspermia was a fringe idea, almost as fanciful as the ancient myths. But as science progressed, pieces of this puzzle began to surface. In the 19th century, some scientists, peering through their telescopes and pondering the origin of life, entertained the thought. In 1903, the Swedish chemist Svante Arrhenius proposed that microscopic spores could ride on the pressure of starlight, literally sailing on beams of sunlight from one world to the next. To him, space was not an insurmountable void, but a medium across which life's tiniest forms might drift like cosmic dandelion seeds. His radiopanspermia idea suggested that life could hop between planets over eons. At the time, these notions were speculative, and many of his peers were skeptical. How could fragile life endure the deadly cold, vacuum, and radiation of space for thousands or millions of years? It seemed far-fetched. Yet nature has proven that life can be astonishingly hardy. We have discovered bacteria that can enter a state of extreme hibernation, enduring intense cold and dryness for centuries. Tiny creatures like tardigrades, also known as water bears, have been shown to survive the vacuum of space, enduring harsh solar radiation and near absolute zero temperatures, then reviving when returned to a hospitable environment. If some life forms on Earth can do this, it's not impossible that microbes embedded in rock could survive a long journey through space. Inside a meteorite, layers of rock might shield a spore from radiation, like a natural spaceship carrying its passenger safely inside. Indeed, evidence of the building blocks of life arriving from space is well established. Meteorites that have fallen to Earth have been found to contain amino acids, the fundamental molecules that make up proteins in living organisms. One famous example is the Murchison meteorite, which landed in Australia in 1969. It was found to harbour a variety of amino acids and other organic compounds, some of which are very rare on Earth. These molecules likely formed in the cold depths of space, in interstellar clouds or nascent solar systems, long before the meteorite arrived here. If non-living chemistry can be ferried across the stars, could actual life do the same? Scientists have also found that comets and icy bodies contain organic molecules. The Rosetta spacecraft, which visited comet 67P Churyumov-Gerasimenko, detected carbon-rich compounds on the comet's surface. Such findings suggest that the chemistry needed for life is not unique to Earth. It's spread throughout our solar system and likely the galaxy. Perhaps early Earth was showered not just with water from comets, but with complex organics, contributing to the emergence of life. This idea that space delivered the ingredients of life to Earth is sometimes called pseudo-panspermia or soft panspermia. Even if whole organisms didn't arrive, the seeds, the raw materials, might have. But panspermia goes a step further, suggesting entire living microbes, not just prebiotic chemicals, made the journey. Is there any direct evidence for that? Not yet. We have not found an unequivocal alien microbe in a meteorite. However, there have been intriguing hints and claims. In 1996, scientists announced they had found possible microfossils in a Martian meteorite known as ALH 84001, a rock ejected from Mars that landed in Antarctica. Under the microscope, they saw structures that resembled bacteria and chemical signatures that might hint at life. For a moment, the world buzzed with excitement at the thought that life on Mars might have been found, and that it travelled to Earth within this rock. Over time, most of the scientific community grew skeptical of this claim, finding that the evidence could also be explained by non-biological processes. But the fact remained pieces of Mars have indeed journeyed to Earth. If Mars had life billions of years ago, it's conceivable some of it could have come here. In fact, at least 100 Martian meteorites have been discovered on Earth, meaning material is exchanged between planets. Similarly, impacts on Earth have likely lofted rocks into space that eventually fell on Mars or Venus. Our worlds are not closed systems. They swap bits of themselves across the void. This interplanetary swapping opens the door to the possibility that life, once started on one planet, could spread to others in the same solar system, a concept known as lithopanspermia. Perhaps life first sparked on Mars when it was warm and wet, and later caught a ride to a then young Earth, seeding our planet. Or life began here and seeded Mars, or both were seeded from a third source. We simply don't know yet, but it is a tantalizing possibility. Even in modern times, we've seen hints of how life might travel. Some hardy microbes and tiny creatures called tardigrades have survived exposure to open space on the exterior of spacecraft. In 2019, when a lunar probe carrying dehydrated tardigrades accidentally crashed on the Moon, it may have spilled these virtually indestructible water bears onto the lunar surface. They were not actively alive during the journey, but the incident shows how life's stowaways could hitch rides beyond Earth. Those tardigrades are likely inert on the Moon, but it sparks the imagination to think that simple life forms might voyage between worlds, waiting for conditions to awaken them. Expanding the scope beyond our solar system, the distances become immense. But nature still finds a way to surprise us. In 2017, astronomers detected an object moving at high speed on a trajectory that clearly originated from beyond our solar system. The first confirmed interstellar visitor, named Oumuamua. It was unlike any comet or asteroid we had seen before, a mysterious elongated shape tumbling through space, visible only as a faint point of light moving against the stars. Oumuamua came and went quickly, but its very existence proves that material can travel between stars. Not long after, another interstellar object, Comet Borisov, was discovered passing through our system. If rocks and ice can voyage across the gulf between stellar systems, one can imagine that life's spores might hitch a ride on or inside them. Maybe most such journeys are doomed, the passengers perishing in the long night. But all it would take is one surviving fragment carrying life, and a new world could be inoculated with the essence of a biosphere from light years away. The panspermia hypothesis has profound implications. If it is true, it means that life in the universe could be related, that we might share common ancestry with organisms on distant planets, because long ago we had the same parent world, or exchanged life through cosmic collisions. It paints life as a tenacious traveler, finding a way to bridge the vast emptiness. It also means that the origin of life might be incredibly rare, perhaps happening only once in a billion galaxies. But given the right circumstances, that spark gets distributed, lighting many flames from one initial fire. On the other hand, if life can start easily on its own, panspermia might be just one mechanism among many to mix things up across space. Either way, it underscores that we are connected to the cosmos in a literal way. The atoms in our bodies come from stars, and perhaps the spark of life itself is a shared legacy among the stars. Despite its romantic appeal, panspermia remains unproven. Skeptics point out that we have no conclusive evidence of life arriving from elsewhere. Every living thing we've ever tested is connected on the same tree of life, suggesting a single origin, at least for all Earth life, rather than multiple introductions from outside. If alien microbes had sprinkled in over time, maybe we would see different biological lineages. We have not. at least not yet. Additionally, the journey is truly arduous. The radiation in space is deadly over long times. Without sufficient shielding, DNA and cell structures degrade. The cold and vacuum cause dormancy, but also chemical damage. So the odds of survival over millions of years in interstellar space are slim. Panspermia might be possible in principle, but extremely rare in practice. Yet researchers keep the door open, because life has a way of defying expectations. Experiments have shown some spores can survive years in orbit, and microbes have been found alive inside meteorites that sat in space. We continue to examine space rocks for signs of biosignatures that don't match Earth life, and missions like the Perseverance rover on Mars search for ancient life that might hint at a shared origin with Earth life, or a second genesis. If someday we find life on Mars, or another neighbour, the question will arise: did it evolve independently, or are we cousins? Scientists will scrutinize any alien biology for clues. If, say, Martian microbes use DNA with the same genetic code as Earth's life, that could suggest a shared origin via panspermia. But if we discover organisms with an entirely different biochemistry, perhaps using unfamiliar amino acids or genetic molecules, it would point to a separate origin, a true second genesis. Either outcome would revolutionize our understanding of life's place in the cosmos. There's also a provocative offshoot of panspermia, the idea that perhaps life on Earth was deliberately seeded by an intelligent civilization elsewhere. This is called directed panspermia. It sounds like science fiction, and it essentially is, at this point, a speculative notion. Yet even this has been seriously considered by a few scientists. The late Francis Crick, co-discoverer of DNA's structure, once pondered whether the complexity of the genetic code might suggest an origin beyond Earth. Perhaps spores sent in a spacecraft by benevolent aliens seeking to start life in the cosmos. There's no evidence for this, but it shows how profound the mystery of life's origin is, that such ideas are entertained. Whether by natural means or hypothetical alien intent, the concept underscores our longing to know if our existence is part of a larger cosmic story. Today, as we send our own spacecraft out, we face a related question. Are we contaminating other worlds with our microbes? Lander probes to Mars or the moons of Jupiter are carefully sterilized, but we cannot be absolutely sure we haven't carried earthly bacteria there. In a sense, humanity might unwittingly become an agent of panspermia, spreading Earth life wherever we go. Perhaps one day we will do so intentionally, terraforming a barren world with microbes to prepare it for larger life. What was once the realm of myth, life springing from the heavens, could become a matter of choice and technology. For now, the panspermia hypothesis remains one of the great unsolved cosmic mysteries. It ties into the age-old questions: is life an earthly fluke or a cosmic norm? Did we originate here, or are we the children of distant stars? As we look out into the galaxy with telescopes and space probes, we search for signs that life took root elsewhere. A molecule in an alien atmosphere, a fossil on Mars, a strange signal from afar. Any of these could hint that life is not confined to Earth. And if we find life out there, panspermia will be one of the puzzles to solve. Are we looking at a stranger, completely unrelated to us, or at a long-lost cousin that shares our origins? In pondering life's cosmic journey, we come to realize how precious and remarkable life is. Whether life began here or arrived from afar, the mere existence of living cells, defying the void of space, speaks to a universe that can breed complexity from chaos. Life connects us to the cosmos in a very real way. We are pieces of the universe, that can contemplate itself. Now, if life could indeed spread among the stars, it raises a further question. Could life also flourish into intelligence elsewhere? If the seeds of life are everywhere, perhaps some seeds grew into forests of intelligent beings under alien suns. And if there are other civilizations out there, why do we see no sign of them? The night sky above Earth is vast and ancient. We have tuned our ears and eyes to the cosmos, expecting to hear echoes of other minds. Instead, we are met with a great silence. This mystery, the eerie quiet of a seemingly lifeless universe, despite the potential for many worlds of life, is what we turn to next. Why, in a cosmos that could be teeming with life, do we find the skies so silent? The stars continue to shine in silence. When we consider the sheer number of those stars, it seems impossible that they are all lifeless. The Milky Way galaxy alone holds around 300 billion suns. Many of those suns have planets. Astronomers have already found thousands of these exoplanets. By all odds, a good number of them should be Earth-like, with rocky surfaces and temperate climates, perhaps oceans and atmospheres where life could thrive. If even a fraction of those worlds birthed life, and a fraction of those in turn evolved intelligent beings, the galaxy ought to be teeming with voices and wonders. And yet, as we peer into the cosmic night with our telescopes and antennas, we find no trace of anyone else. As far as our instruments can tell, we might be utterly alone. Why? This haunting question lies at the heart of what we call the Fermi paradox. The paradox is named after physicist Enrico Fermi. In 1950, during a casual lunch discussing UFO reports and the possibility of interstellar travel, Fermi suddenly asked, "Where is everybody?" It was a simple and profound question. If the universe is filled with countless stars and presumably countless civilizations, why haven't we seen any sign of them? His colleagues chuckled, but the question stuck. Over the years, it grew into a central puzzle in cosmology and astrobiology. The more we learned about the cosmos, about its vast age and the commonness of planets, the more pointed Fermi's question became. Not long after Fermi's remark, astronomer Frank Drake attempted to frame the problem in scientific terms. In 1961, he introduced what is now known as the Drake equation, a way to estimate the number of detectable civilizations in our galaxy. The equation strings together several factors. How many stars form each year? What fraction of those stars have planets? How many of those planets might develop life? How often life might evolve intelligence? And what portion of those intelligent beings might create technologies that send signals into space? Finally, it includes the crucial factor of how long such civilizations might broadcast their presence before either falling silent or ceasing to exist. The Drake equation doesn't give a single answer. Instead, it's a tool to think about the uncertainties. Plugging in optimistic guesses, one might conclude there should be a multitude of civilizations sharing the galaxy with us. Using more pessimistic values yields perhaps 1 or 0, meaning we could be alone. The exercise highlighted just how much we don't know. One term in particular, the average lifespan of a technological civilization, can dramatically sway the outcome. If most civilizations quickly self-destruct or lose interest in communicating, the galaxy could remain quiet even if life is common. In essence, Drake's formula helped scientists discuss the Fermi paradox in a systematic way, but it didn't solve the mystery. To this day, all we have is the contradiction Fermi noted. High probability, but no evidence. When you gaze up at the night sky and see thousands of stars, it's natural to wonder who might be looking back. But so far, we have no confirmed signal, no artifact, no footprint of an extraterrestrial intelligence. Our searches, though increasingly sophisticated, have met only silence. Radio telescopes have been listening for decades for any pattern or whisper that might indicate an artificial broadcast, a message from minds beyond Earth. Projects like SETI, the search for extraterrestrial intelligence, have scanned the sky for anomalies in radio waves, looking for a carrier wave or a series of pulses that stand out against the cosmic background noise. There have been a few tantalizing moments, but nothing conclusive. One famous event was the WOW signal detected in 1977 by a large radio telescope in Ohio. It was a strong, unexpected signal that at first glance looked like what a deliberate transmission from an alien source might resemble. It lasted for a full 72 seconds and then vanished, never to repeat. The astonished scientist monitoring the data scribbled "Wow" next to the reading, giving the signal its name. To this day, no one knows for sure what caused it. It didn't correspond to any known astronomical object or familiar Earth-based interference. It remains a singular, teasing hint, exciting, but insufficient as proof. Scientists tried for years to catch it again or find an explanation, but came up empty. Without repeat detection, the WOW signal sits as an enticing question mark. Was it an alien greeting? Or just an odd natural radio fluke, or earthly signal bouncing in an unexpected way? We simply don't know. We haven't limited our searches to radio. As technology advanced, we expanded our eavesdropping on the cosmos. We've looked for brief flashes of laser light that might be used by distant intelligences to communicate. We've monitored stars for odd brightness changes that could indicate huge orbiting structures. In 2015, a star called KIC 8462852, better known as Tabby's star, made headlines because it dimmed and brightened in irregular, puzzling ways. Some speculated that perhaps a gigantic array of solar collectors, a kind of Dyson swarm, was partly blocking the starlight, an engineered megastructure built by aliens. It was a wild idea born of desperation to explain the data. Over time, the evidence pointed instead to dust clouds or other natural phenomena as the cause of the dimming. Like many times before, a once exciting hint of aliens turned out to have a prosaic explanation. The lesson repeated itself. Extraordinary claims require extraordinary evidence, and so far, that evidence has not materialized. It's worth noting that our search has barely scratched the surface. The galaxy is immense, and our strategies cover only a tiny portion of it at any given time. Imagine trying to detect a particular conversation happening in a vast city by using one microphone from miles away, and the conversation might be on a channel you're not tuned to. We could easily miss signals. Our radio telescopes can best detect strong, intentionally beamed messages directed at us. If alien civilizations are broadcasting mainly to their own networks, or using narrow, aimed communications, like we use focused beams for our satellites, we might never intercept them unless by chance. And the radio part of the spectrum is just one method. Who knows? A civilization might communicate in modes we haven't discovered or mastered, like neutrino beams or quantum signals. It's as if we've been searching one small band on an entire orchestra's range of instruments. The silence might simply mean we haven't listened to the right station yet. Time is another factor. Humanity has only been a detectable presence in the galaxy for a brief moment. Our earliest radio transmissions have been leaking out for about a century, which means they've only travelled 100 light-years or so. The Milky Way is about 100,000 light-years across. If an alien civilization 1,000 light-years away aimed a signal at us in the 18th century, it would have arrived before we had any receivers to notice it. If they sent it in the year 2500, It hasn't arrived yet. We might be like two fireflies flashing their lights in the night, but hundreds of miles apart, unaware of each other. The cosmic timeline has to align just right. Civilizations could be plentiful, yet isolated in time, their lives too short or too staggered to ever connect. It's a sobering thought that even if life is common, the universe's vast scales of space and time might keep us effectively lonely. Given the uncertainty, a host of explanations have been put forward to resolve Fermi's paradoxical question. One is simply that we are indeed alone, or at least the only intelligent, technological species in our galactic neighborhood. This is the rare Earth hypothesis. It proposes that while microbial life might pop up in many places, the path from a single-celled organism to a tool-wielding, radio-building civilization might be so improbable that it has happened only here. Perhaps it took an exceptionally rare chain of events, a stable star, a planet just at the right distance, a big moon to stabilize our tilt and tides, just enough water and carbon, the right timing of asteroid impacts to spur evolution without extinguishing it, and a good dose of luck on top. In this view, multicellular life, complex ecosystems, and intelligence could be vanishingly rare. Earth could be a freak occurrence, a garden oasis in a vast desert. The silence out there would then simply reflect that nearly all other worlds are still and quiet, or home only to simple life forms that don't build radio transmitters. Another possibility is that life and intelligence are not so rare, but intelligent civilizations tend to self-destruct or fade away quickly. The universe is old, about 13.8 billion years, and our galaxy is about 10 billion years old. There has been plenty of time for other civilizations to rise, but time can also wipe things away. A society might flourish for a few thousand years and then collapse, leaving little trace detectable across light years. Think about ancient humans. The people of Mesopotamia or the Indus Valley built cities and empires. But today, we only know them from buried ruins. If we were in another star system now, looking at Earth with a telescope, we'd have no evidence those civilizations ever existed. Now scale that up. A star could host a civilization that lit up its planet for a few millennia, and then it disappeared. By the time its light reaches us, we might see nothing unusual. Some scientists worry that advanced civilizations might have built-in expiration dates. Perhaps they invent weapons of mass destruction or alter their planet's climate irreversibly, and a kind of cosmic entropy ensures that none last long enough to meet each other. From nuclear war to pandemics to artificial intelligence run amok, one can imagine many ways a civilization could tragically end itself. If this pattern is common, the galaxy could be littered with the ashes of societies that bloomed and died too swiftly to ever overlap. We, in our youth as a technological species, might simply be one of the lucky ones, alive at the right time, but maybe destined to face the same pitfalls. The notion that every civilization might carry the seeds of its own end is grim, but it would certainly explain a quiet cosmos. There's also the possibility that we are among the first. The universe needed time to produce the ingredients for life, the heavy elements forged in stars. For billions of years after the Big Bang, planets like Earth were rare because the cosmos was still building up complex elements. Now, roughly 14 billion years into cosmic history, conditions might finally allow many intelligent civilizations to emerge. Perhaps humanity is lucky to be at the vanguard, one of the first voices to develop. The galaxy might be mostly quiet, simply because it is still early in the dawn of intelligence. Perhaps humanity is lucky to be at the vanguard, one of the first voices to develop. The galaxy might be mostly quiet, simply because it is still early in the dawn of intelligence. If this is true, then in time the silence will fade as other civilizations light up the cosmic stage. And we stand now in the precious solitude of a universe that has only just awakened. This idea of inherent hurdles or roadblocks to long-term survival is sometimes generalized into the concept of a great filter. The great filter could be a step in the progression from simple matter to advanced life that is extremely unlikely or difficult, so most attempts fail. It might be behind us, meaning we passed it. Perhaps the leap to life from chemistry is so rare that it almost never happens, and we are one of the few lucky outcomes. Or it could be ahead of us, a looming challenge that nearly all civilizations fail to overcome. We don't know what the filter is, or if it even exists, but the silence in the sky hints that something might be trimming down the number of galactic civilizations. If it's behind us, we might actually be a very special exception, explaining our solitude. If it's ahead, then the true test for humanity lies in our future, learning how to survive our own technologies and impulses to become a long-lived, spacefaring species. In either case, the idea of a great filter reminds us not to take our existence for granted. Of course, there are also many who suspect that perhaps the universe is not silent at all. We just haven't noticed the signals properly. It could be that extraterrestrial civilizations are out there, but they are choosy in how they communicate. Some might broadcast only in directions toward their own colonies or allies, and not in all directions like a beacon. Others might rely on communication methods that are practically invisible to us. It's possible that what we interpret as natural background noise could contain coded messages that we have yet to decipher, or maybe advanced beings are deliberately avoiding drawing attention to themselves, for reasons only they would know. This brings us to another conjecture, the zoo hypothesis. Imagine that a very advanced civilization became aware of us at some point, perhaps by detecting our radio signals or observing our planet's biosphere, and decided not to interfere. Just as wildlife researchers might quietly observe animals in a reserve, these aliens could be quietly watching Earth without announcing themselves. The idea is that they want to let us develop naturally, without the shock or influence of knowing about galactic neighbours, at least until we reach a certain level of maturity. If that's true, the silence could be an imposed one. We're essentially in quarantine, or being gently studied from afar. While there is no concrete evidence for this scenario, it provides one more possible answer to Fermi's question. We haven't heard from aliens because they intend it that way. On the other hand, maybe the silence is a choice that every civilization makes for itself, out of caution. This is the dark forest scenario. It imagines the galaxy as a dark, quiet forest, where each civilization is like a hunter trying to stay hidden. They remain silent because they fear that if they shout out their presence, something might find them, possibly something hostile. It's a paranoid outlook, but perhaps not unreasonable from an alien perspective. They don't know what's out there, and they consider it safer to listen and observe, but never to announce themselves. If all advanced life thinks this way, then everyone ends up sitting silently, wary of drawing attention. The cosmos could be full of life and mind, yet each island of civilization keeps its lights low and its radios quiet. And thus, from our vantage point, we hear nothing. It's a sobering thought that the quiet might be a sign of universal fear. Alternatively, perhaps one bully of a civilization prowled the galaxy in the distant past, eliminating or subjugating anyone who made a peep, and the rest learned to keep their heads down. It sounds like science fiction, and indeed it is at this point, but until we gather more data, we cannot fully dismiss even the unsettling possibilities. Meanwhile, some wonder if the paradox might be answered by the idea that extraterrestrials have already visited Earth in secret. Over decades, numerous UFO sightings and tales of alien encounters have captured imaginations. Could it be that aliens are here, and the skies are silent because they observe from the shadows, or even walk quietly among us? As fascinating as these stories are, science requires extraordinary evidence for extraordinary claims, and such evidence is lacking. Investigations into UFOs have so far revealed no confirmed spacecraft or artifacts of alien origin. Most sightings turn out to be misidentified natural phenomena or human-made objects. Those few cases that remain truly unexplained are tantalizing mysteries, but not proof of cosmic visitors. Without concrete proof, these accounts remain part of folklore and speculation, rather than a solution to Fermi's question. They do, however, show how deeply we yearn for connection with other intelligences. There is also the humbling possibility that we are looking for the wrong signs entirely. We assume that an alien civilization might use radio or visible light, or build big structures, things we can detect. But a truly advanced species might transcend these crude technologies. They might merge with machines, or shift their consciousness to virtual realms, living out existences in contained digital universes and having little interest in the physical cosmos. They might achieve a level of understanding that makes the external universe irrelevant to them, appearing almost invisible. Alternatively, life elsewhere could be so unlike us that we wouldn't even know it was life. Imagine beings made of energy, or organisms living inside stars, or neutron stars, or intelligence embedded in the fabric of spacetime. These speculative forms might not communicate in any way we can perceive. If we encountered their works, we might not recognize them as technology or life. In such a scenario, the universe could be humming with intelligence, and we are simply not yet equipped to notice it or comprehend it. Until we have evidence one way or another, we are left with our imaginations and whatever hints the cosmos provides. At times, the silence can feel almost deafening. We send out our own messages now, like the Voyager spacecraft carrying a golden record of Earth sounds and images, drifting out of the solar system, or deliberate radio messages beamed at nearby stars. And we wonder if they will ever be answered. Perhaps someone is out there sending their own Voyagers, and one day, eons hence, one will wash up in our solar system to be discovered. Or perhaps the only voices in this galaxy are the faint echoes of civilizations long gone, their ruins too far to ever reach us, and their signals having long since dissipated. And yet, despite the silence, we do not lose hope or curiosity. The very emptiness inspires us to fill it with our questions and our quests. In a way, the Fermi paradox is as much about us as it is about aliens. It asks how we will face the cosmos if it truly is empty, and equally how we would handle it if it's not. Either answer, that we are alone or that we are one of many, has profound implications. If we are alone, then the duty to cherish and propagate life falls solely on our shoulders. We carry the flame of consciousness for the entire galaxy. If we are not alone, then there may be wisdom or caution in the silence that we have yet to understand. For now, we continue scanning the sky for a glimmer of communication. New telescopes and projects are coming online, capable of detecting possible signatures of technology in the atmospheres of exoplanets, or faint whispers from distant stars. Each year, our searches become more sophisticated. We listen, we watch, and we even send our own tentative hellos into the void. The night sky above, once the province of myth, now is a subject of rigorous observation, but it still holds the power to stir our imagination. We may feel small and alone under the silent stars, but we also feel a deep connection to them. The paradox remains unresolved, a question mark hanging over our place in the universe. It teaches us humility and patience. It reminds us that there is much we do not know, and it sparks in us a sense of wonder and cautious anticipation. Perhaps tomorrow, or a year, or a century from now, the silence will be broken by a signal, a discovery that shatters our solitude. Or perhaps, in the silence, we will find our own way forward, carrying life to the lifeless and becoming the answer to Fermi's question for someone else in the far future. Contemplating the Fermi paradox leads us naturally to reflect on the vastness of the stage upon which this drama unfolds. Whether the universe is empty or filled with others, we are compelled to ask, just how big is this cosmos that can contain such solitude? Where does it end, if it ends at all? And what lies beyond the furthest frontier we can ever see? To address the mystery of the silent skies, we must also confront the mystery of the endless skies. Now, we turn to the ultimate horizon, the edge of the universe, and what, if anything, lies beyond. High above the earth, the sky seems endless. But is the universe itself endless? It's a question that stretches our imagination to its limits. For centuries, we didn't even know if there was a boundary between Earth's atmosphere and space. Now we routinely send rockets beyond that thin blue line. But when it comes to the cosmos as a whole, we still wonder, does space go on forever? Or is there some kind of edge? If we had a magical spaceship that could travel unlimited distances, would we eventually come to a sign that says, end of universe, no farther beyond this point? Or would we just keep going and going through an infinite expanse of stars and galaxies? Let's imagine taking that fanciful journey. We launch into the cosmos and travel for millions of years. We pass galaxy after galaxy, and still new ones come into view. We voyage for billions of years more. If the universe is infinite, this journey would never encounter a barrier. Stars and galaxies would continue indefinitely, growing ever more distant and faint, but never running out entirely. If instead the universe is finite and curved like a globe, our far future explorers might eventually find themselves approaching familiar constellations from behind, having looped around the cosmos without knowing it. In practice, of course, we cannot undertake such a trip, but through science, we try to discern the true nature of the cosmos from right here on our tiny world. Our best understanding today is that the universe does not have a conventional edge, like a wall or boundary where things abruptly stop. What it does have is an observable edge, a limit to what we can see. This limit isn't set by a physical barrier, but by time and the speed of light. The universe began about 13.8 billion years ago in an event we call the Big Bang. Since then, light has had 13.8 billion years to travel. That means we cannot see any object farther away than light could travel in those 13.8 billion years. Actually, because the universe has been expanding all the while, that distance is much larger, roughly 46 billion light-years in radius. Think of it this way. The observable universe is like a sphere centered on us. We are at the center of our visible bubble, not because we're special, but because we can only see as far as light has come in the time since the cosmos began. Every year, this horizon inches outward as light from a bit farther reaches us. But we will never see beyond a certain point, because beyond that, light hasn't had enough time to get here yet. It's as if we're standing on a tiny island in the middle of the ocean. We can see out to the horizon in all directions, but no further. We know there's likely more ocean beyond our sight, but it's invisible to us. What lies beyond our cosmic horizon? Probably more universe, more stars, more galaxies, more of the same vastness that we see locally. There's no reason to think the universe suddenly stops being there past the distance we can observe. Those far regions are simply beyond our view. They are too distant for their light ever to have reached Earth in the history of the universe so far. They might eventually become visible as time goes on. Except there's a catch. The universe is expanding. Not only that, the expansion is speeding up due to a mysterious phenomenon we call dark energy. This means distant galaxies are receding from us, and the farther away they are, the faster they appear to be moving. In fact, beyond a certain distance, space is expanding so quickly that light from those regions will never reach us. The space between is widening faster than the light can cover it. Essentially, those regions are not just out of sight, they're out of reach forever. As time passes, more and more of the universe will slip beyond our observational grasp. Distant galaxies that we can see today will, billions of years from now, redshift into darkness, their light stretched beyond detectability, until our distant descendants, if any, might see only a few neighbouring galaxies and nothing else. The observable universe is a temporary gift. We happen to live at a time when we can see an abundance of galaxies around us. That view won't be as rich in the far future. So, is there an edge of the universe? From our perspective, the edge is this horizon beyond which light hasn't reached us. It's not a physical edge, and if we could somehow magically teleport beyond it, we'd likely find more universe, not an abrupt end. The universe could be infinite, extending without end in all directions. If that's the case, it has no edge at all. It just goes on forever, like an endless plane. On the other hand, the universe could be finite, but unbounded. This is a tricky concept to picture, but a common analogy is the surface of a sphere, like the Earth. The surface of Earth is finite. If you travel long enough, you can come back to your starting point, yet it has no edge where you fall off. In a similar way, space could curve back on itself in a higher dimension. If you set off in a straight line in such a universe, you might eventually return from the other side. Though in practice, if the universe is that shape, it's so enormous that a full circumnavigation would take far longer than the age of the universe, so it's not something we could observe. Current measurements of the geometry of space suggest that it's very flat on large scales, which if taken at face value implies it's either infinite or so vast that we haven't detected any curvature. Cosmic inflation theory supports this idea. It proposes that a tiny fraction of a second after the Big Bang, space itself expanded exponentially, like a balloon inflating in an instant. This would stretch any curvature to near flatness and make our observable patch just a minuscule part of a much, much larger cosmos. If inflation is correct, the universe could be far larger than what we see, perhaps effectively infinite. So the simplest answer many cosmologists favour is that the universe is effectively infinite in extent. If that's true, then asking what's at the edge of the universe is like asking what's north of the North Pole. It's not a question that has a sensible answer, because an edge doesn't exist in the way we intuitively think of edges. If space truly extends forever, then beyond our horizon, there could be endless galaxies, and perhaps even repetitions of cosmic patterns. In an infinite expanse, every possible arrangement of matter would occur somewhere. That means far beyond our sight. There might be regions startlingly similar to our own. Maybe even another star with planets much like ours, purely by chance. Infinity is a strange concept, implying that the universe could hold not just vastness, but all possibilities played out over and over. However, even an infinite universe can have limits in other ways. For example, there was a limit in time, the Big Bang, beyond which we cannot see into the past. That's like the edge in time, rather than in space. We also have the edge presented by the cosmic microwave background. This is the afterglow of the Big Bang fireball, now cooled to just a few degrees above absolute zero and stretched to microwave wavelengths. When we look out into space, we are also looking back in time. The farther away an object is, the older the light we see from it. Eventually, we look so far away, and thus so far back in time, that we reach a point when the universe was young, hot, and opaque, about 380,000 years after the Big Bang. Before that time, the cosmos was a dense plasma that no light could freely travel through. It was like a fog. The cosmic microwave background, CMB, is essentially the glow from the moment the universe became transparent, stretched to microwaves by billions of years of expansion. It appears to us as a nearly uniform background of microwave light, with tiny variations that reflect the seeds of galaxies. We can't see with light beyond that wall of the CMB, because earlier than that, light was trapped. In that sense, the CMB is like a foggy glass that obscures what came before. It's not a solid edge, but it's a limit to our vision nonetheless. We're trying to circumvent that by other means. For instance, neutrinos or gravitational waves might give us a glimpse of the universe even closer to the Big Bang moment, since they can penetrate the plasma. But as of now, the CMB is the farthest surface we can see. It's sometimes poetically called the edge of the observable universe, though beyond it lies the truly unknown. So, what lies beyond the observable universe? If space is infinite, then simply more galaxies, more space, more everything, stretching out without end. If space is finite and wraps around, then if you somehow went far enough, you'd eventually loop around, as peculiar as that sounds. But what about beyond space itself, if that even makes sense? Humans have a hard time with the concept of nothing or outside of everything, because by definition, if something is outside the universe, can we even call it a place? It would be beyond space and time as we know them. Some theories, however, suggest that our universe might be just one bubble in a frothy sea of universes, a multiverse. In these ideas, space, and perhaps different forms of space-time, might exist outside our own universe's boundaries. Our universe could have bubbled off from a larger meta-universe during the Big Bang, or there could be infinitely many other universes, each with their own laws of physics or values for fundamental constants. This is highly speculative, and by nature might be forever beyond our ability to test, since other universes, if they exist, might be completely disconnected from ours. But it's one way scientists and philosophers have tried to grapple with the question of what, if anything, is outside the universe we see. One idea, called eternal inflation, imagines new universes constantly forming like bubbles in a vast cosmic foam. Our Big Bang would have been one such bubble, nucleating and expanding, surrounded by countless others that are forever out of reach. In this view, what we call the universe is just one island in an infinitely larger sea of universes, Another profound question about edges comes when we consider time. If we think of the Big Bang as the beginning of the universe, one might ask, what happened before the Big Bang? Was there a time before time began? This is a bit like asking what's beyond the edge of a map when the map covers the entire globe. Classical Big Bang theory would say time itself began with the Big Bang, so the question may be meaningless. There was no before because time didn't exist yet. But some newer theories suggest there could have been something before, perhaps a previous universe that collapsed and rebounded, a cyclic universe theory, or a quantum foam out of which our universe tunneled into existence. We don't know the answer. Our physics breaks down when we try to probe the instant of the Big Bang or anything prior. It remains one of the most tantalizing mysteries. The edge of time, the moment of creation, and whether anything lies beyond it. Standing here, as living beings on a tiny planet, we confront these enormous questions with a mixture of awe and humility. Our ancestors once imagined physical edges to the cosmos, a firmament, or a dome, or a great waterfall at the world's end. Today, our cosmologies have expanded far beyond those early visions. We envision a universe governed by general relativity and quantum mechanics, a universe that might be infinite, or at least unbounded, with dimensions and shapes that challenge common sense. Yet, in some ways, we circle back to familiar feelings. We still find ourselves on a kind of island in the midst of an unfathomable ocean. The difference is, we know the island is Earth, and the ocean is the vast universe, stretching 46 billion light-years in all directions, and likely far beyond. We strain our eyes to see farther, to learn more, pushing our technologies to extend our reach. We send out satellites to map the faint glow of the cosmic microwave background, looking for clues about what lies beyond our horizon. We build larger telescopes to see the first galaxies that formed, hoping to press against the veil of the early universe. Each time we extend our reach, the edge moves a little further, revealing new wonders, but also new questions. Will we ever truly know if the universe is infinite, or if there's something beyond the cosmic horizon? It's possible that some answers will remain forever out of reach. The observable universe might be all we can ever observe, by definition. And if so, our knowledge will have a hard boundary. But human curiosity doesn't easily take no for an answer. If we can't see something directly, we try to infer it indirectly, through theory and through subtle fingerprints in the data. Already, by studying the shape of the CMB's temperature fluctuations, scientists can deduce that if the universe curves back on itself, it does so on a scale far larger than what we can see. That hints at a much bigger cosmos than our observable patch. We might never see those far realms, but we can gather that they exist. It's like knowing that there are more oceans over the horizon by observing the swells that reach our shores. Considering the edge of the universe, or lack thereof, can be as dizzying as contemplating the Fermi paradox or the origin of life. It forces us to reckon with infinity and eternity, concepts that we can't fully grasp, but that we can feel in a tingling way when we stare at a clear night sky. In truth, the most honest answer to what lies beyond the observable universe is, we don't know, and we may never know. There is always the possibility of the unknown, further layers, deeper truths, hidden just out of reach, and that is perhaps fitting. The universe, if it were a simple thing with a neat boundary and a label saying the end, might be less wondrous than the open-ended expanse we find ourselves in. Because it has no clear edge, it always invites us to push further, to ask the next question, to peer around the next cosmic corner. As we reach the end of our journey through these unsolved cosmic mysteries, we find a common thread running through them all: our own sense of wonder and curiosity. From the ancient myths of creation to the scientific theories of panspermia, from the lonely silence addressed by the Fermi paradox to the unimaginable expanses at the edge of the universe, we humans have grappled with the unknown by telling stories, by gathering knowledge, and by imagining what lies beyond our current understanding. Each mystery we explored, how life began, and whether it came from the stars, why we haven't found other intelligences, what the ultimate limits of the cosmos are, leaves us with more questions. And that is a beautiful thing. The unknown is not just something to fear or solve. It is also what gives us purpose in exploration. In the calm darkness of a clear night, when you look up, you might feel the depth of these mysteries. The stars whisper ancient light into your eyes. You might picture the gods and heroes that ancient people saw, or ponder if someone out there might be looking back, or wonder what lies in the darkness beyond what even our telescopes can view. Our journey through the unknown universe is both an outward voyage to the edges of reality and an inward journey into our own love for knowledge. It's a reminder that we are a part of this universe, made of its star stuff, and driven by a desire to understand. We conclude now, not with absolute answers, but with a gentle reverence for all that we have yet to learn. The universe is vast and largely uncharted, but we have brought it a little closer through our questions and insights. The mysteries we've discussed remain unsolved, but they are not unsettling terrors. They are invitations to keep searching. The cosmos holds its secrets close, but every year we unravel a few more threads. Perhaps one day, far in the future, our descendants will find that life truly is everywhere, or that other minds share the galactic island with us, or even discover how our universe came to be and what lies beyond its horizon. Until then, we find meaning in the quest itself. In the end, the unknown universe may never be fully known, and perhaps it shouldn't be. Its mysteries inspire us to bond together in our small world, to work and wonder, to gaze upward in unity. In that sense, the darkness between the stars is not empty at all, but filled with possibility and promise. As our exploration comes to a close, we can let the quiet of the cosmos wash over us, not in despair at its vastness, but in gratitude that we are witnesses to its grandeur. The story of the universe is still being written, and we are a part of it. Under the silent, sparkling skies, we gently close this chapter of discovery, content with the knowledge that the adventure of seeking answers will continue as long as humanity dreams.